Today on How It's Made. Photographs, putting you in the picture. Fur tanning, hair care secrets revealed. Welding electrodes. You'll want to join us for this one. And electric violins. Making these is a fiddly operation. But first... In the 1830s, the first photographers used light-sensitive chemicals to capture images on paper. Today, machines do much the same, but with amazing speed, accuracy and versatility. In this digital age, there are still many who stick to this tried and tested method. The photo lab receives envelopes containing rolls of film for developing. Processing will turn each exposure into a negative image, then a positive one. That positive is what we know as a photograph. A scanner takes a digital photo of the order details specified on the packages. It tracks things such as the print size and finish, and the number of copies that have been ordered. A conveyor then sorts the envelopes into bins, grouping them with similar orders. Next, a machine extracts the film rolls from the metal capsules in total darkness. Exposing the film to light would ruin the photos. The envelopes go into bundles, so they can be later reunited with the right pictures and negatives. Here's what the machine looks like on the inside. A blade cuts open the metal capsules, and another slices off the leader. The machine unravels and lines up as many as 60-metre-long films end to end. A sticker joins the ends and identifies each film with a barcode. The machine measures the assembled strip, then winds it onto a reel inside a metal box. Another machine unwinds the reel and runs it under an infrared light so that a technician can check it for tears. Just one tiny tear could jam the machine and ruin all the photos. If a tear is found, it's repaired by hand. The technician makes the repair in total darkness. First, he applies tape to reattach the area. Blades then cut the tape evenly on both sides. The technician is able to see what he's doing on a TV monitor hooked up to an infrared camera inside. Developing the exposures requires 4 chemical baths, still in complete darkness. In the first, sulfates make the image appear as a negative. The second includes acetic acid to halt the effect of the sulfates. The last 2 baths preserve the image and rinse away chemical traces. To print the pictures, the negatives are loaded into yet another machine. This one contains light-sensitive paper. All it takes is a flash to transfer the image. A sensor instantly adjusts the intensity to correct any improper exposure by the photographer. To develop the prints, the paper goes through 4 chemical baths, similar to those used for the negatives. One bath reveals the image. Another stops that process, and 2 more preserve the image and rinse off the chemicals. This time, however, the paper then heads into an oven to dry for 2 minutes at 70 degrees Celsius. Now, a technician marks the pictures that are too bright, too dim or out of focus and removes them for redeveloping. Next, a machine unwinds the strip, scans the barcodes and cuts out the pictures that belong together. It also cuts the negatives into numbered strips of 4. The photos and negatives are slipped into an envelope. The computer shows just what to include, and the machine provides the film's original package. When you get your photos, you can check them against your original order, so you can make sure that everything's picture perfect. Fur was first worn to keep people warm, before for some it became a fashion accessory. Tanning is the process which turns a pelt into leather. Today the process is much as it has always been, and the furs still provide old-fashioned warmth. These beaver pelts have been purchased at auction. They're sorted and the quality of the hair is inspected to determine the type of garment they're suitable for. A lot number is hammered into the underside of the pelt. It perforates the skin. This technique is used so that the number stays on the pelt during processing. The ear cartilage is cut out using a pneumatic punch. It's important to get rid of the cartilage early on to enable the pelts to pass through machines during the tanning process. The pelts are slightly dry because of preservation techniques used before they were delivered to the tanning plant. So they're put through various chemical washes to rehydrate them. The final bath contains tanning chemicals which convert the underside of the animal skins to leather. The supple leather texture will eventually allow the pelts to be shaped into garments. Between each wash, the furs go into a wringer. It spins out the excess liquid. All that moisture has caused the pelt to thicken, so they thin it down with a spinning blade called a flesher's knife. You need to be an expert to wield this tool. One false move and you'll cut into those follicles and lose fur. Next, sawdust is shoveled into a large drum. The pelts are placed in the drum along with the sawdust and a mineral solution is added. The drums turn, tossing it all for about half an hour. This cleans and conditions the leather side of the pelts. The furs are still damp when they emerge, so they are hung over wooden dowels to dry, leather side up. The rest of the sawdust will fall away in subsequent operations. Now the pelt's long hair is scraped off to expose the downy undercoat. This undercoat has a more desirable look and texture. A generous amount of oil is rubbed into the leather to lubricate it. Then the pelt is tossed into a kicker box, and you can see where it got its name. The kicking action causes the oils to penetrate the skin. Next, a spinning metal wheel tugs at the pelt to stretch it. The ragged edges are cut away. Then it goes into a hot press. This irons and adds luster to the fur. After a quick brush, the pelts get one more press. Then a shearing machine cuts the hairs to an even length. They bundle up the pelts for a trip to the garment factory, where they'll be great design material. Coming up on How It's Made, welding electrodes. We'll join up with the makers of these clever gadgets. And electric violins. They're loud and they're proud. See you after the break. More than a century ago, welders first fused two metal surfaces by melting a metal stick over them using an electric current. That stick is known as a welding electrode. Farmers and mechanics often use this useful tool to repair heavy machinery. This company's electrodes are coated with powdered metals and minerals. During welding, the metals melt and the minerals protect the area from oxygen, which would weaken the bond. The electrode transmits an electric current that heats and melts both the electrode and the metal surfaces, welding them together. Thin metal wire forms the electrode's core. The type of wire changes dependent on what the electrode's designed to weld. In most cases, the core is made of carbon or stainless steel. A machine simultaneously spins and bends it, reshaping the wire till it's completely straight. 4 metal rollers then push and guide the wire into a guillotine. The blade chops the wire into segments that will become the electrode cores. The factory puts a variety of metals and minerals in the coating. The metals include nickel, manganese and iron. The minerals, alumina, magnesia and limestone. They also add a colorant to identify the different models. Workers mix the ingredients with a little glue until they turn to the consistency of wet sand. A worker then packs the mix into a machine that forms it into slugs with a hole down the middle. He adds a plastic cap. Then a metal cover slides on and the machine takes over. It takes only a minute for the machine's piston to compress the powder into a solid. To put the powder coating on the core wires, a worker loads 4 slugs into an extrusion press. It'll apply 120 tons of pressure to shoot the powder through nozzles that'll coat the wires as they pass through the holes in the slugs. To load them into the press, the wires are first stacked in this feeder. The opening at the bottom can be adjusted because core wires have a range of different diameters. These rollers pass them through the press one at a time. Four wheels then pull the wires from the feeder into the extrusion press for coating at a rate of up to 1,000 electrodes every minute. When the coated electrodes emerge, they hit a metal wheel that positions them on a conveyor. A sander removes up to 5 centimeters of coating from the bottom where you grip the electrode, and it bevels the tip so it conducts electricity even better. A worker now checks for uneven coating and to see if the wire's well centered. The coating dries at room temperature for up to 72 hours. To cure the coating, the electrodes are put in an oven and heated to 485 degrees Celsius for up to 5 hours. Once they've cooled, the electrodes head into a printing press. An ink wheel prints the model and the type of current that's required. Another ink wheel then applies a colour to the gripping end. It's another way to identify the model in case the lettering on the side rubs off in storage. From there, it's off to packaging. An optical scanner counts the electrodes. Then a stacking machine separates them into bundles. Finally, they're inserted into cardboard canisters. A piece of cardboard is added to compress them tightly for the trip. A sticker marks the contents, and tape keeps the package tightly sealed. And to that, we say well done. The invention of the electric violin was all about turning up the volume. In the big band era, the sound of the traditional violin was overpowered by the horns and drums. Amplifying the violin changed everything. Suddenly, the violin wasn't just background sound, it was part of the show. The electric violin comes in different shapes because it doesn't rely on the body to resonate sound. This craftsman builds the violins one piece at a time, starting with the neck. He traces the shape onto a piece of maple. Then he outlines the top plate. Walnut is used for the bottom part, or lower bout, as well as for the backbone of the violin. Next, a bandsaw is used to cut out the shapes. The more precisely the cuts are made, the less sanding will have to be done later. The dimensions for the top and neck are exactly the same as for a traditional violin, so there won't be any difference in the reference points the violinist relies on. The lower bout has a unique design. And the head is more streamlined than a traditional violin. There's no decorative scroll. Next, a cavity is chiseled out of the head of the violin to create the peg box. Parallel grooves are carved into the back to give it a snazzy look. A rasp is used to shave the wood to the correct thickness. Holes for the turning pegs are drilled into the side of the peg box, one for each of the 4 strings. After the grooves on the back have been filed a little more, the rest of the neck is scraped to give it a final finish. The peg holes are tapered using a tool called a reamer. The ebony pegs have matching tapers, so they fit snugly into the holes. Everything is checked to make sure it measures up. Wood glue is brushed onto the neck section, and the ebony fingerboard is pressed onto it. Surgical tubing holds them together while the glue dries. 2 assembly holes are drilled in the top piece, and corresponding holes are made in the other parts. A sander smooths the edges of the backbone. Then, a high-speed router is used to bevel the lower bout piece to give it a clean edge. The wood is stained. The loud colours seem appropriate for these high-volume instruments. A crystal has been glued into the violin's wooden bridge. to generate electricity from the string's vibrations and create sound. The wire from the bridge is pulled through the backbone, and then the bout is mounted to the backbone. An ebony chin rest is bolted on top. Next, the neck is attached to the rest of the assembly. The ebony tailpiece is looped on. A string is pulled from the tailpiece to a peg. The act of tightening the first string raises the bridge, which will be held in place simply by tension. Now it's time to hook up the violin to the amplifier and let the music tell the rest of the story. So, whether you're keen to get a look at those holiday snaps, or you want to keep warm, caveman style, or prove what a bright spark you can be with metal, now you know how it's made. Today on How It's Made. Glass bottles. Clearly fascinating. Hacksaws. We're off to a tool factory that's a cut above. And ice hockey goalie masks. Making them is a face-saving endeavour. But first, glass is made of natural ingredients that are abundant. Making it uses less energy than producing metal or plastic, and it can be endlessly recycled. Whether they're coloured or clear then, glass bottles and jars are always green. The recipe for glass combines several natural raw materials. The main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It makes up about 15%. A limestone content of about 10% makes the finished glass more durable. These ingredients are combined with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. After 24 hours at 1500 degrees Celsius, a gooey liquid that's the consistency of honey is produced. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical globs. Each glob is the exact amount required to make up one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar-forming and bottle-forming machines. A glob of molten glass goes into a preliminary mould. In a matter of seconds, it comes out as a miniature version of the bottle, known as a parison. Each parison then moves into a blow mould, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mould cavity. This process creates the final bottle shape and hollows out the inside. These are amber-coloured beer bottles. The colour is produced by adding small amounts of iron, sulphur and carbon to the glass mix. A similar manufacturing process is used to produce other types of bottles and jars. In this run, the company is making 375 millilitre wine bottles out of clear glass. This run is producing bottles also out of clear glass. This mould, though, has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing layer. The bottles cool at a controlled rate as they move through the layer. This gradually releases the stress from the glass. As the bottles exit, they're sprayed with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now line up in single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are moulded correctly. Before shipping, each bottle gets a final visual inspection. The proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that is a clear incentive to recycle. From big saws to jigsaws, handsaws to bandsaws, even backsaws to hacksaws, all these tools have their specific purpose. Hacksaws are chiefly for cutting metal or other tough materials. So what is it that gives them their cutting edge? Hacksaw blades are made from a wide range of steel alloys. Here, a thin band of steel feeds into a machine that cuts it into blanks of 30 centimeters long and 1.3 centimeters high. The blanks are loaded into a jig, 300 at a time, where they're compressed into a block for easier cutting. The block is then fed into a machine called a mill grinder. It cuts teeth into the upper side of the blanks. A water-based lubricant washes away the metal particles. This hacksaw model has a 24-point blade. There are 24 teeth every 2.5 centimeters. A brush is used to remove any metal residue. The quality control department inspects each blade for flaws. Then it's off to the next phase. A separator detaches each of the 300 blades, aligns them, then sends them through a setting machine. The machine bends the teeth to either side at a slight angle. This is called offsetting. It will enable the blade to clear away particles as it saws, preventing it from jamming. Now it's time to harden the teeth. The factory does this by heat treating the metal. A worm gear aligns the blades to enter a heating coil. In this process, the electromagnetic heating coil heats the teeth to temperatures as high as 1200 degrees Celsius, depending on the type of metal. This takes no more than 2 seconds. After the blades exit the heating coil, the surrounding air cools them down over the next several hours. This phase is called air quenching. The blades are now ready for printing. An offset printing press applies ink to raised lettering on a cylinder. That cylinder transfers the ink to strips mounted on another cylinder. These strips then print the company name, the blade length, and the number of teeth per inch on the side of the blades. Now, a machine inserts the blades in groups of 5 into slots, called fingers. The fingers rotate the blades and place them on a conveyor belt. The machine raises the blades and tapes them together at one end. This makes it easier to transport them to another part of the factory, where production continues. Next, the hacksaw's frame, the component that holds the blade, is made. The frame's components are placed in a jig that's positioned on a rotating carousel. A robotic welder fuses the components. A press punches 3 holes in the handle for attaching a foam or plastic grip. The 2 halves of the grip are fitted into a sonic welder that fuses them using high-frequency sound waves. The sound waves create friction at the seam, and this generates enough heat to melt the parts together. Now the frame is ready for the blade. An automatic device tightens a wing nut to put tension on the blade. Randomly selected blades receive a final quality control check. The testing machine cuts through a block of stainless steel. The machine performs this test 6 times per blade. Then the computer calculates the average number of strokes. If that average falls within the norms for this particular model, the batch gets the thumbs up. Keeping those thumbs, of course, well clear of the blades. Coming up on How It's Made, it's a 2-part special looking at how you can save face on the ice. Jolly hockey sticks. See you after the break. It's not just their protective shell and cage. Their wild paint jobs are designed to intimidate. Incredibly, back in the 1960s, the first goalies to wear masks were ridiculed by fans who viewed them as a sign of weakness. Today, though, ice hockey goalie masks are all about putting on a brave face. These masks allow the goaltender to play it safe, so they're far less likely to be sidelined by a serious injury. Production begins with a plaster mold of an average person's face. The mouth hole is plugged with plasticine. This ensures that the mold won't leak when it's filled with plaster of Paris. It's left to dry for half an hour. Then, the initial mold is pulled off to reveal the solid impression. Plasticine is pressed onto strategic areas. This mimics the foam safety guards that cushion every mask. The final result is called a plug, and it will be used to make a 2-part compression mold. After a black sealer is applied, it's polished smooth, eliminating imperfections that will be visible on the mold that will be made from it. Over at another station, fiberglass fabric is unrolled and cut into sheets, which are layered. A pattern is drawn on the top sheet. Spacing the shapes closely together minimizes waste. The goal is to create 100 masks from one roll of material. A disc cutter slices through 25 layers of the fiberglass fabric. Then, various composite fabrics are stacked, including several fiberglass ones and patches of Kevlar for reinforcement. Kevlar can absorb so much impact, it's used to make bulletproof vests. More fabric is placed over the Kevlar. An epoxy resin is spread onto each layer. They are draped over a mold that's been made from the plug. And the material is smoothed to eliminate air pockets, as they are then layered and glued. The ragged edges are trimmed away. Then, the inside portion of the mold is placed into the outside one. The wet fabric is now sandwiched between two mold pieces. A 1-ton press is lowered to compress the layers of fabric, as the resins between them continue to form a bond. Clamps are added to keep things tight. After 20 minutes, the laminated fiberglass shell is prized from the mold. The shell is now extremely rigid. It's the raw form of a goalie mask, but it still needs a lot of work, so it's over to the trimming and grinding station. A trim jig is placed over the shell. A high-speed router is used to cut an opening for the cage. The flash is sliced off with a disc grinder. The edges are sanded and ground. Holes are drilled, which will be used to attach various fasteners. Larger holes are carved out. These aid ventilation and reduce the mask's weight. The mask is almost complete, but it still needs a snazzy paint job. The makers of ice hockey goalie masks have turned safety into an art form. The mask has become a canvas for some very bold designs and colours. It's a psychological tactic to intimidate the other team, and it scores points with the fans who like the cool paint jobs. The mask is roughed up with an orbital sander to prepare it for painting. Then a sealer is poured into a container. The technician wears a safety mask because the emissions are toxic. He adds the activator solution and a reactive reducer and stirs the sealer together. Then he sprays the sealer mix onto the masks. The finish will cure and harden as the chemicals in it generate their own heat. Next, a vivid gold base coat is sprayed. Computer graphics are sent to a plotter that cuts out adhesive vinyl paint masks. Any unneeded vinyl around the stencil is pulled away. This process is called weeding. Then, the vinyl stencils are pressed against the mask, and the paper backing is peeled off. Applying a stencil to the crown is tricky because the surface is curved with ridges, so it doesn't lay flat. The technician lifts and cuts the pattern with a utility knife and then straightens it out. This mask is starting to look impressive. But the whole thing is covered with white paint. It's a temporary cover-up. This process is all about layering patterns and colour. More vinyl shapes are applied. Then, using a pressurized paint system, everything is sprayed bright red. Next, an artist airbrushes some shadowing on the now barely visible image of a leaf. Some of the vinyl is peeled away. The surface of the mask is sprinkled with water. Paint is misted over it, and the water droplets catch the paint. It's blasted with a heat gun. The water evaporates, but the paint dries in droplet form, giving the mask a frosted look. A drop shadow is airbrushed around some lettering. The technician dispenses with the usual safety gloves for this detailed work. And now, all is revealed. The vinyl is peeled away. Any flaws are touched up. The technician traces the pattern onto see-through paper and then transfers it onto board. He cuts it out with a utility knife. Then he aligns it with the shape on the mask and precisely airbrushes around it to make the smudge disappear. With the final clear coat, this mask makes a colourful statement. And now it's time to put all the pieces together. The stainless steel cage is screwed on. A little glue is applied to reinforce the adhesive-backed foam cushioning. The sweatband is attached with Velcro so it can be removed and washed. The harness is threaded through the backplate to the front of the mask. The harness is elastic, so it gives the mask some flexibility. Now it's ready to go out on the rink. And these completed masks scream, the puck stops here. So, whether you're after a bottle for your favourite tipple, or you want a little cutting-edge technology, or you need to save face on the ice, now you know how it's made. Today on How It's Made. Lacrosse sticks. Making them is a spectator sport. Frozen fish products. We have the cold hard facts. Torches. We shine a light on them. And paintbrushes. A report that will have you bristling with excitement. But first, lacrosse is North America's oldest sport. It was back in the 1400s that people started playing with a distinctive netted stick. French missionaries decided the stick resembled the staff-like crozier or cross carried by bishops. And so, the game became known as lacrosse. Lacrosse has never been more popular than it is today. To make a lacrosse stick, a hickory log is split down the middle. This tree was cut in the autumn when the sap is out. The log is subdivided into 8 pieces. Each piece then goes through a bandsaw, which trims it to a width of 5 centimeters. Hickory is used because it's tough and can withstand the high-impact game of lacrosse. But it needs to be softened up, so the sticks are steamed for 45 minutes. Then, the hickory sticks are placed in a jig. In this steamy state, the wood is flexible, and one end is curled around a form. A wire is looped around it, so it will hold a crook-like shape while the wood dries for 1 month. After that, the other end is steamed, placed in a jig and bent back just below the crook. This is called the back bend. It's set on a rack to dry and harden. This is the basic form. As you can see, it resembles the bishop's crozier, the one that inspired the name of the game. After 2 weeks of drying, the stick is ready to be carved. Using a drawing knife, the bark is shaved from the stick. It's sculpted to make it thinner, following the bends of the stick. It's a skilled job that requires years of experience. Next, holes are drilled in the curve of the stick, 21 in total. Then it gets a heavy sanding. The surface has to be absolutely smooth, so the player won't get any splinters. Linseed oil is rubbed into the stick to prevent the wood from getting too dry. The brand name goes on. And now it's time for the weaver to build the side wall of the net. In the old days, they used raw hide for this, but today they weave with nylon string. He interlaces it with leather runners that have been threaded through the holes at the back bend. He brushes polyurethane on the completed side web to stiffen it. Next, he attaches the other end of the leather runners to the top of the crook. The player will be able to change the depth of the netted pocket to his or her preference. He interlaces the leather runner weave with the nylon sidewall. And then pulls the woven pocket over a post to give it some shape. He loops the ends of the leather runners in a half hitch and snips off the excess. Every detail of this lacrosse stick has been handcrafted. It's a process that has taken 3 months. So now, let the game begin. Might be better with more than 2 of you though. Since prehistoric times, the Inuit have used quick freezing to preserve fish. They threw their catch onto the Arctic ice to instantly freeze it. It wasn't until the early 20th century that the rest of the world discovered that this was better than slow freezing. It's a case of progress moving at a glacial pace. Fish that's rapidly frozen right on the ship better retains its flavour and texture. This is minced cod frozen solid. It underwent quick freezing in China and was shipped in this frozen state all the way to this Nova Scotia facility, where it will be turned into fish sticks. The fish blocks are loaded into a machine. A powerful ram forces the blocks through knives, which slice them into logs that are 48 centimetres in length. The logs are loaded vertically into slots. Below, more knives slice the logs into sticks. 85 fish sticks will be produced from one log. They check for breaks as the sticks move to the next station. At another production line, quick frozen haddock fillets are dumped into a big steel hopper. It funnels them to a flighted conveyor. Each bunch is dropped onto a vibrating table. The vibrations separate the fillets as they move into lanes and shuffle down to an inspection station where flaws can be easily spotted. Now, it's time for a hot shower. It lasts just a second. The hot water melts the fillet's protective glaze, but doesn't thaw the fish itself. Deglazing allows the coating mixture to stick to the fish. The fish sticks then travel through a curtain of batter made of flour, water and spices. The excess collects in a pan below and coats the bottoms of the fish sticks. Back on the haddock production line, they're loading a toasted wheat blend into a machine called a breader. It creates a thick shower of crumbs below that coats the fillets evenly as they journey through. Then, the breaded frozen fillets head for the fryer. The fish sticks go through a fryer too, for 28 seconds, just long enough to cook the outside coating, but the fish remains frozen on the inside, creating what we all know as fish fingers. With the coating baked on, the fish fingers and fillets are now en route to the freezers. Meanwhile, on a third production line, oil and red peppers go into a high-speed mixer. Some parsley is added for seasoning. While it steam cooks, it's stirred by hand. The red pepper sauce cascades from an applicator, saturating these frozen fillets. This coating sticks without being fried, so the fillets head straight for the spiralling freezer. The fish fingers and breaded haddock are in similar freezers. After 45 minutes, the haddock slides down a chute, which weighs it into portions. Heated jaws seal the backs. An oscillating feeder deposits the fish fingers into boxes. One last inspection and they're ready for the shops. The peppered fillets are vacuum packed and this meal is sealed. And now, no matter where your tastes lie, there's plenty of fish to fry. Coming up on How It's Made, we shed light on the production of torches. Before brushing up on our knowledge, of DIY tools. See you after the break. The torch can illuminate any situation. The first version was invented in the late 19th century. It produced only flashes rather than a constant beam, hence the name flashlight. Today, they're rather more sophisticated, so let's shine a light on their production. The torch shows us the way when things look dim. To make a military torch, they place an aluminium bar in a computerized lathe. Blades go to work and shape it into a torch body. As a drill hollows out the bar, coolant flushes over it to prevent the metal from expanding as the tooling heats things up. This blade cuts threads on the outside, so they can screw on a torch lens cap later. A gripper now pulls out the tube so tools can work on the back half. A blade slims that section down and then carves a cross weave onto it. This heavy texture will make the torch easier to grip. Next, a hole is drilled into the torch's tail stud. It's an attachment for the wrist strap. After the torch body has taken shape, it receives a black protective coating. Next, using tons of force, a machine injects hot plastic into a mold which forms the lens for the torch. The lens is placed in a jig and the mold core unscrewed. The core has formed threads in the lens so it can be screwed onto the torch body later. Another injection mold is used to make plastic torch bodies. The plastic torches are for more general use than the aluminium ones. For custom orders, a logo is stamped onto the torch using a hot foil press. Next, light-emitting diodes are inserted into a circuit board. The diodes are electronic lamps that are very bright and used instead of traditional incandescent bulbs. The diodes' wires are soldered to a circuit board and then trimmed. The diodes are now secured and connected to the circuit board. For bigger torches, they use lots of diodes, up to 60 of them for this torch that's being made for search and rescue work. Next, a stamping press shapes the bronze battery contacts. An ultrasonic welder bonds them to a plastic plate. Then a wire is soldered from the diodes to the contacts. The lamp part of the torch is now built. Now, springs are inserted into the aluminium torch bodies. The batteries are loaded and the springs hold them in place. The lamp assembly is slid into the torch cavity and the lens is screwed on. This aluminium flashlight has been put together in a flash. They move on to plastic torches. The battery contact and spring assembly goes in, followed by the batteries. The light-emitting diode lamp is next. The lens is screwed onto the lamp. The plastic glare shield is the final touch. Now these torches are ready to shine. If you've got a paint job to do, the right type of brush can make all the difference. For latex paint, it's best to use a paintbrush with synthetic bristles, such as nylon or polyester. With oil-based paint, it's best to use bristles made of natural animal hair. So let's brush up on our knowledge. For natural bristles, this factory uses pig hair imported from China. It arrives in bundles, sorted by length. Each paintbrush contains up to 5 different lengths. This bristle structure makes the brush sufficiently stiff. All 5 lengths go into a specially designed mixing machine. First, it combs the bristles, straightening them out and removing any curved hairs. Then it spreads the bristles flat and mixes the lengths together. Now, a worker takes a handful of bristles from the mixer and pats them on a vibrating table. Like human hairs, animal hairs have a root and a tip. The vibrations make all the butt ends line up flat. Each handful goes into a storage box until it's time to install the bristles into the ferrule, the steel band that goes around the paintbrush. This machine makes the ferrules. It shapes a thin steel strip 3 to 4 centimeters wide. Rollers imprint beads to make the strip more rigid, and a herringbone pattern that is purely cosmetic. Then a blade cuts the strip into pieces that are long enough to wrap around the brush. The machine bends each piece around a forming horn, then joins the ends in a strong lock seam. Hammers flatten the seam and the ferrule is finished. Back to the bristles. A brush-making machine will join them to the ferrules. Workers load the mixed batches of bristles into one of the machine's feeders and the ferrules into the other. The machine picks up the required amount of bristles. Transfer jaws grab the tips and insert them into a ferrule. A vibrating device called a patter pushes the bristles in straight. A continuous strip of cardboard feeds the next part of the equipment. The machine parts the bristles, cuts off and slots in a piece of cardboard. This centerpiece creates a well inside the brush head to help hold the paint. The machine then pulls the bristles out to the proper length, leaving about ½ centimeter inside the ferrule. Workers pick out the loose bristles. The lightweight paintbrush handles are made of plastic pellets. A vacuum loader sucks the materials up to a molding machine, which melts the pellets at 205 degrees Celsius. The machine then injects the molten plastic into handle-shaped molds. 5 minutes later, the machine ejects the handles from the molds. Workers attach 30 handles at a time to sticks and hang them across paint vats. The handles are then lowered into the paint slowly to avoid creating air bubbles. The first coat is a primer. After half an hour, the handles are ready for the next coat. This time, the vat contains coloured paint. It dries to a matte finish in 30 minutes. The third vat contains clear lacquer. This coat protects the paint and makes the surface glossy. Now it's time to glue the bristles to the ferrules with strong epoxy glue. It seeps down into the bristle base. Workers now load the finished brush heads and handles into an assembly machine. The machine inserts a handle into each brush head, shooting 2 to 3 nails into each side to secure it. Finally, A printing machine stamps the company name onto one side of each handle. Paintbrushes come in a wide range of widths and thicknesses, providing different strokes for different folks. So, whether you're a sporty type looking for the best equipment, or a hungry fella looking for a fishy feast, or you're lost in the dark and in need of enlightenment, now you know how it's made. Today on How It's Made. Deep cycle batteries. How it's made goes on a power trip. Tins. It's a can-do approach on this production line. And optical lenses. We focus on their manufacture in a two-part special report. But first, deep cycle batteries are found in a variety of vehicles, like trains, boats and forklift trucks. Whereas a car battery provides a quick surge of current to start the engine, a deep cycle battery provides a steady amount of current over a long period of time. Let's charge over to the factory. Deep cycle batteries range from 2 to 48 volts. Their power is generated by cells, a group of lead plates coated in lead oxide and acid. This casting machine produces lead grids that will become the plates in the power cells. The machine pours molten lead into grid-shaped molds. Water circulating through the mold hardens the metal in just 5 seconds. The machine casts 2 types of grids, negatives and positives. The next machine coats the grids with a chemical paste that contains lead oxide and acid. The positives get one paste formulation, the negatives a different one. The grids are now called plates. Workers stack them in cases, alternating positive and negative, then drop them into tanks of sulfuric acid to charge. The lead oxide and acid in the paste store the power. After charging for 24 to 72 hours, depending on the model, the plates go into a machine that washes them 3 times to remove acid residue, which if left, would corrode the metal. The charging process blackens the plates, which are now called dry charge plates. A machine wraps each positive in glass strand matting, an insulation material similar to fiberglass, then in a plastic envelope. These coverings protect the plates from short circuits. Workers stack the plates again, positive, negative, positive, negative. This time though, each stack contains a specific number, from 5 to 33 plates, depending on the battery model. Each stack will become one cell. A cell provides 2 volts of electricity. Each plate has a tab. A robotic machine cleans the tabs with a wire brush and a chemical solution called flux. Then, it dips the tabs in molten tin. This tin coating will improve the bond when they solder the tabs together. The robot wipes the tabs on a flux-imbued sponge to clean their surface once again, then drops the cells into a mold containing molten lead. This solders the tabs together, bonding the plates within each cell. The process casts 2 lead posts on the cell's positive side and 2 on its negative side. These posts will connect the cells and build the required voltage. Next, Each cell goes into a polypropylene casing called a jar. Each cell is tested to make sure it functions properly. This also shows if the cell is positioned correctly in the jar, so that the positive and negative signs on the cell cover will be on the corresponding posts. The cover is heat sealed and the protruding posts are sealed with lead. Air is pumped into the cell and soapy water is brushed over the cover to test the seals. Any bubbles indicate a gap that needs to be resealed. In another part of the factory, various small components are moulded from molten lead. Among those parts are the connectors that link one cell to another. Workers weld them to the posts. These are 8-volt batteries, so for each one, they connect 4 cells inside a polyethylene case. Now that assembly is complete, the case cover goes on. These rubber grommets keep water from seeping inside and shorting the battery. Now the inside is filled with sulfuric acid, which functions as an electrolyte, the medium that helps the lead in the plates conduct electricity. The tin can was invented back in the 1800s. To preserve and protect. We still rely on this trusty container to keep a range of perishables fresh. Everything from food to blood plasma to military supplies. After all these years of use, the tin can still has an airtight reputation. It's time to lift the lid on this traditional container and get the inside story from the factory. To make a tin, they take a strip of tin steel and weld it to join the ends. The resulting cylindrical shape is the body of the tin, and it's about to be hermetically sealed. The rotating tools on this machine stretch out the edges of the cylinder, forming a flange. They top off the tins at this station, where a spinning head presses the cylinder into these lids. It simultaneously rolls the flanged edges together to make an airtight seal. This container is for classified military use. But over on another production line, they're making a more standard tin, the kind you would put coffee in. So this assembly is more mechanized. In a fraction of a second, an automated welder rounds and joins the metal to create the body of a tin. The tins travel forward and upward on a magnetic conveyor system. They're going to the other side of the plant, where they'll get tops and bottoms. This kind of tin has a reusable slip cover lid and gets some decorative work. A punch cuts out designs that have been pre-printed on metal. At the same time, it pushes the cut design onto a die to form the lid shape. A magnetic conveyor pulls them forward and flips the lids to stack them for packaging. Elsewhere in the plant, they're making cans to go with some other lids. A lineup of circular blades slices through tin sheets. The cut pieces accumulate in stacks. They load the flat pieces of tin into a cylinder where they're curled into tubes. As they exit, robotic arms make seams in the rolled tins, and a press applies force to lock them. This lock seam is an alternative to the welded one we saw earlier. Now, another magnetic conveyor pulls the tin tubes forward. And they go for a spin, while rollers flange the edges so that the bottoms can be attached. A punch cutter makes the bottoms. The scraps will be recycled. The can bottoms spin out of the punch cutter before landing on the next magnetized conveyor. They get a squirt of liquid rubber, which will harden into a gasket to prevent leaks in the can. A folding machine now locks the bottoms to the tubes as they spin. More than 12,000 cans per hour can be made on this high-speed line. From a blank piece of steel to a very useful container. Whatever their contents, these tins are destined for a full life. That is until someone decides to empty them. Coming up on How It's Made, it's a two-part special focusing on optical lenses. See you after the break. In Focus. It's time to turn our camera's eye on the camera's eye. Optical lenses are really several lenses combined into a single unit. Together they recreate an image by bending light rays so they converge into a common point, called the focal point. Get the picture? These television camera lenses start with a very precise design. A diamond blade slices up a block of specially selected optical glass, while coolant prevents the blade from burning it. The slices then go under a diamond drill, which cuts several discs from one glass slice. The operator is careful to keep waste to a minimum. Optical glass is extremely expensive. During the drilling, the optical glass sits on a thinner piece of glass covered with wax. As the wax is melted, the discs are easily pulled away. Next, a device spins one of the discs while a wheel overhead sculpts it into a lens. The operator checks each lens for chips, and this one looks smooth. This tar-like substance is called pitch. The edges of the lenses have been built up with tape to contain the pitch. They completely coat the underside of the lens with it. Several pitch-covered lenses are now in a metal shell. A worker picks up a hot aluminium dome called a blocking body. He presses it onto the pitch-covered lenses and the pitch melts onto it. Dousing it with water causes the pitch to harden, sealing the lenses to the blocking body. The blocking body is now upside down and acting as a holding device as it oscillates on a spinning grinding shell. The grinding makes the surface of the lenses uniform and smooth. They place a polisher on the lenses. It's lubricated with a very fine abrasive. For about an hour, the polisher oscillates while the block spins. Polishing makes the lenses smooth and transparent. It also gives them an even more curved profile. The lenses have been removed from the block, and it's time to cut the diameter down to size. Using a microscope, a technician centers a lens between two brass chucks. A diamond blade at the back cuts the lens as the technician monitors it. He's making sure the diameter and axis of the lens have a common center. Next, they group lenses on racks called planets. Their universe is a vacuum chamber. The technician closes the door, and the planets continue their orbit. Inside this vacuum, an electron beam evaporates coating materials. The vapor rises to give the lenses a protective coat. A computer monitors the coating process. But there's more to come. This process really gets visual as all the pieces of the camera lens come together. The optical lens is the ultimate image maker. Along with cameras, you'll find them in projectors, microscopes, and X-ray equipment. They give us a close-up view of so many things. It seems only appropriate that we take a close-up look at the optical lens itself. The lenses have just spent 3 hours getting a protective finish. It's time to wipe away any residue and make sure they're perfect. This particular lens is concave. A technician covers it to protect it while she cleans and inspects a lens with the opposite profile, convex. Then, the convex lens goes to another technician who places it in a holding device. He looks into a microscope and adjusts the position of the lens until it's optically centered. He uses wax to keep the lens from shifting in the holding device. They give the lens another cleaning. Each one must be absolutely spotless before they proceed to the next step. Otherwise, dust particles could become trapped within the optical system and affect image quality. Now that the surface of the convex lens is immaculate, she dabs optical cement onto the center of it. She gives the other concave lens a little more scrutiny before she cements it to the convex lens. She applies pressure to spread the cement between the two lenses. Cementing them together means they'll be less likely to shift around in the lens barrel. She checks for dust one more time. Then it's under the microscope for an optical alignment of this double lens. Because the cement isn't yet dry, this technician can push the top lens around and adjust its position. Next, they prepare the barrel that will hold the lenses. A technician traces out lettering using a stylus. attached to a sharp tool that engraves information on the lens barrel. It prints technical details that will tell the photographer just what the lens will do, like the focal length, the f number, and the size of the aperture opening. These reference points allow the user to pull a picture into focus at the desired magnification. Now, they double-check the design for this complex optical system and begin to pull all the pieces together. This singlet, or single lens, goes into the metal barrel first. Other lenses with various curvatures and dimensions follow. Metal spacers are placed between the lenses to separate them. Proper spacing will prevent aberrations in the image, such as blurring. Between installations, the barrel is covered with a piece of lint-free plastic, because eliminating dust continues to be a necessity. One fleck could ruin this entire assembly. The last lens is coaxed into the barrel. A retaining ring to hold the stack of lenses is installed and locked into place. There's one final inspection. The assembled optical lens is examined from all angles. It takes a total of 6 weeks to make one of these optical lenses, and in the end, it's picture perfect. So, whether you're looking for a little power boost, or you need a container that definitely can do the job, or you want a posh bit of kit to bring things into focus, now you know how it's made. Today on How It's Made. Horseshoes, trotting out the equine footwear. Dishwashers, we visit a factory with a spotless record. Graphite fly rods, this story is sure to lure. And frozen pizzas, defrosting the secrets of how they're made. But first, horses first wore leather and metal shoes around 500 AD to protect their hooves from wear and tear. A farrier is someone who makes horseshoes and applies them carefully. Today they're usually made of steel, aluminium or plastic. So let's trot on and see how they're made. A horse's hoof has a hard outer wall like a fingernail, only much thicker. The farrier attaches the horseshoe to this wall with heat and lead nails. The horse feels no pain because the nails don't reach the sensitive tissue inside. Horses get new shoes about every 5 weeks. After removing the old ones, the farrier uses a file to trim the wool's growth since the last change, about 10 millimeters. He measures the hoof's contour, marks the measurement on a steel bar, and cuts it to size with a rotary saw. Steel is the material of choice because it's affordable and durable. Next, he heats the bar until the middle's white hot. He brushes off any dirt, then dips the bar in water to cool it. Then he hammers the ends to redistribute the metal towards the middle. This widens and thickens the part of the horseshoe that gets the most wear, since the front of the hoof hits the ground first and hardest. After reheating the bar, he hammers it again, this time with no cooldown. For larger shoes, two farriers take turns hammering, so that they can shape the steel while it's still hot and pliable. Using a drafting compass, the farrier gauges where two grooves for nails will go. He reheats the bar, then holds a sharp-ended tool against it while another farrier drives it in with a hammer. The nails won't protrude when they're embedded in the grooves. These areas will also fill with dirt to give the horse traction. The farriers round the sharp edges of the horseshoe so the animal won't cut itself when it's lying down. They make the nail holes by first driving this tool into the grooves. Then they use another tool to perforate the steel, hammering it into the shoe over an opening in the anvil that lets the tool pierce through. The farrier then repeats these steps on the other side. It takes two farriers about 15 minutes to make a pair of horseshoes. The first farrier heats one shoe, while the second hammers the other. Like the hooves, the front and back shoes are differently shaped. The front pair are rounder, the back ones are more oval, because the horse's hind hooves have evolved to dig into the ground for traction. The farriers also hammer part of both curves, flattening the edges into raised sides called clips. These help the shoe fit onto the hoof. For larger workhorses like Clydesdales, the farriers bend the ends downward to give the feet more traction. It's not uncommon for a 900-kilogram horse to have to pull twice its weight. Now time for the fitting. After heating the shoe, but not as much this time, the farrier uses it to melt the outer part of the wall. This makes an imprint that later helps him place it properly on the hoof. Horses first wear shoes at about 3 years old, the age when they start working or competing. The farrier fine-tunes the fitting with a metal filing tool, curving the edges further to make them even safer for the horse. Next, he shines the steel with a metal brush. Depending on the foot size, the finished shoe can measure anywhere from 7 to 25 centimeters across. Now to attach the shoe. The farrier first files the hoof to remove any dust or sharp edges. He slips on the shoe, then gently hammers as many as 3 nails into each side. The nails are about 5 centimeters long. They're made of lead, a metal that's easy to bend. And that's what he'll do after hammering them through the wall. He clips off the ends and bends the rest in towards the wall. Then he uses other tools to gouge small crevices in which to bury the ends. This makes it easy to straighten out the nails and yank off the shoe when it's time. He also hammers the hoof against a template to stabilize the shoe. Next, he files the hoof, and finally, the horse is ready to stroll. When it comes to horse footwear, it's all about function, not fashion. So whether you've got a pony or a stallion, make sure the shoe fits. In 1886, an American, Josephine Cochran, built a motorized wheel with wire compartments for dishes, turning inside a copper tank filled with soapy boiling water. But it wasn't until the 1950s that domestic dishwashers came on the market. And arguments about who did the dishes were gone forever. Building a dishwasher starts with a watertight container called a tub. Some high-end models have stainless steel tubs. The rest have tubs made of molded plastic, usually polypropylene. Workers screw 2 pairs of plastic wheels to each side of the tub. They'll support the sliders on which the upper dish rack moves. The lower dish rack rolls along the bottom of the tub. This steel frame helps strengthen the tub. They fix a steel plate at the bottom to shield the plastic from the heat of the motor. Then they attach steel legs to the frame. They install a rubber reservoir called the sump. It collects the water that flows to the bottom of the tub. They screw in a two-part ring to hold the sump in place. The heating element is a ceramic insulated iron cable. This filter traps food particles washing off the dishes. After fitting an O-ring seal to make the sump leak-proof, they secure the heating element by screwing ceramic insulators to the protruding connectors. Now for the polypropylene wash arms. This model has one at the bottom, with a tower that juts out for a larger spray span, and a second wash arm at the top. The motor pumps clean water directly to the bottom wash arm, and through this flexible hose to the top wash arm. Once they connect the hose, they spin the wash arm to make sure there's no obstruction. Meanwhile, workers connect key components to the dishwasher's circuit board. This metal box is the timer. It controls the wash and dry cycles. It activates this green lever to trigger the white lever to open the detergent dispenser at the right moment in the wash cycle. The detergent dispenser is located on a plastic panel that will line the dishwasher's door. They call this panel the inner door. The seal will prevent water from leaking out, and it also provides some soundproofing. A press runs over the inner door, driving the seal evenly all around. Now they screw the inner door to the outer door. The assembled door hooks onto hinges at the base of the tub. This machine presses the hook and hinge together so that the door doesn't come unhinged. The dishwasher's motor is relatively quiet because it uses an inherently low-noise induction drive design. The white machine attached to the motor grinds up food particles so that they don't clog up the drain. The last technical step is to connect the various wires. Before applying the finishing touches, workers conduct a seal test. They flush each tub with water to check for leaks. In this portable dishwasher, workers install cement blocks as a counterweight so that the washer won't tip forward when you open the door. And because a portable usually sits in full view, it also needs sides and a top. This top is decorative laminate on medium density fiberboard. They screw it to what's called the wrapper, a three-sided panel made of painted steel that covers the sides and back. A clean look to go with your clean dishes. Now who's going to empty it? Not me. Coming up on How It's Made. Graphite fly rods. We cast our eye over this one. And Mamma Mia frozen pizzas. Yum yum. See you after the break. Welcome back to How It's Made. Graphite is a space-age material, lightweight, flexible and strong. The very qualities that make it useful in space also come in handy at the river or lake. It explains why graphite fly rods are now mainstream in the fishing world. To make one, they start with a sheet of graphite. They cut out shapes following precise measurements. One mistake here and the performance of the rod will be compromised. This will be a 3-piece rod with a butt piece, midsection and tip. They place a shape on a tapered steel mandrel and peel away the paper backing. This machine rolls the graphite shape around the mandrel. They make all 3 sections of the fishing rod the same way. A graphite strip at the end is used for reinforcement. The graphite remains on the mandrel for the next step. They wind polypropylene tape around the graphite to squeeze out any air pockets between the layers. Then it's into the oven to cook at 125 degrees Celsius for about an hour and a half. The tape won't melt, but resins in the graphite will, baking the rolled layers together. Afterwards, they remove the shrink tape and pull the graphite blank off the steel mandrel. Then the rod blanks go for a dip in a special finish, which turns it a deep blue. They bake on the finish for an hour and a half, again at 125 degrees Celsius. Afterwards, they measure the rod sections, cut them to size, and fit them together. Bending without snapping is the graphite rod's strong point. They hot glue the stainless steel tip to the end. Then they piece together the retainer for the reel. This lock nut will allow the reel to be tightened. The butt plug will keep everything from sliding off. They glue cork rings together to make a handle. Then they shape it with a chisel and sandpaper. The line guides go on next. To secure it to the rod, thread is wound around it. A final step ensures the handiwork doesn't unravel. They place the rod in a rotating jig and brush 3 coats of glossy epoxy onto the thread wrap. This not only protects it, but gives it a nice finish. Now, they slide a metal foot into a groove on the reel retainer, and it's ready for the reel to be attached. But before you can cast your line, there is some information that needs to go on the rod, like the brand name and the serial number. A final inspection, and it's almost time to test the waters. The reel snaps into place, and it's easily adjusted with the lock nut. So now all that's left is to cast your bait, sit back and wait, and leave the rest to fate. Millions of pizzas travel daily from the frozen food section of the supermarket to the family dinner table. Thick or thin crust, meat or vegetarian, their convenience makes them a staple in the freezer. But how do they end up tasting so fresh when they start out so frozen? Making frozen pizzas requires a maze of machines. To make the dough for the crust, they combine flour, salt, sugar and yeast with water and oil in a large mixer. They also add cornmeal for flavour. The mixer turns the ingredients for about 4 minutes, kneading the dough. The dough rises for about half an hour. Then they feed it into a chunking machine, which divides the dough into smaller pieces. The chunks travel to a sheeting machine that rolls them into a flat sheet 2.5 centimeters thick. A light dusting of flour keeps the dough from sticking to the machinery. A series of rollers, called quick reducers, gives the dough an even consistency. A flour brush massages the dough, ensuring a smooth surface. Next, stainless steel spikes pierce through the dough with holes 7 to 10 millimeters deep. These holes will stop air pockets from forming in the dough. A large plastic roller with several round forms cuts the circular shape of the pizza crust. The machine automatically separates the leftover dough. The factory remixes it with fresh dough for the next batch. A conveyor takes the dough circles to their next destination, the oven. They bake for 2 minutes between 200 and 315 degrees Celsius. 6 chambers inside the oven automatically control the temperature pattern to ensure that each one bakes evenly. Next stop, the tomato sauce. A tank pumps a steady supply of sauce into a reservoir, drenching a roller, turning inside. A plastic board then scrapes the sauce onto the crusts passing below. The excess sauce drips down, replenishing the reservoir. Mounds of pre-shredded mozzarella are ready to be added. A cheese applicator machine controls the output, so that the mozzarella forms an even layer. Large hoppers load heaps of pepperoni, sausage and other meat toppings into a meat applicator. With the tomato sauce and cheese, the meat toppings cascade down onto the pizza crusts. The pizza is now ready for inspection. Workers take samples off the line and weigh the crust, sauce, cheese and meat to ensure the equipment dispense the right amount of each. Next, the pizzas enter a spiral freezer called a blast cell, where they spend about 20 minutes at minus 31.6 degrees Celsius. An overwrapping machine applies a clear layer of plastic around each pizza, automatically cutting the wrap to fit. A vision control system takes a picture of every pizza, verifying the size, diameter, and checking for any imperfections. The machine automatically rejects any less than perfect pizzas by air blasting them into a separate tub. Finally, an arm pushes each pizza into a waiting box. All that's left now is to heat it up and dig in. Bon appetito. So, whether you're a horse with happy hooves, a contented cook with dishes to wash, or an avid angler looking to catch the best equipment, now you know how it's made. Today on How It's Made. Pistons. This should spark some interest. Paint rollers. We bring you wall-to-wall coverage. Parachutes. A story with strings attached. And chimneys. We smoke out a factory that makes them. But first... Pistons are key to the internal combustion process that drives engines. A piston is a plug that slides up and down inside each cylinder, compressing gas and air ignited by a spark plug. The resulting energy turns the crankshaft and drives the engine. This company makes 9,000 different types of pistons. For everything from dirt bikes to car engines. A piston starts out as a 3-metre-long aluminium rod. Aluminium is ideal because it's a lightweight, rust-resistant and easy-to-cut metal. A rotary saw slices the rod into slugs, the length of which can be changed by adjusting the feeder machine to push the rod at different intervals. This piston model requires 7-centimetre slugs. The factory recycles excess aluminium shavings. The punch press and die are preheated to 426 degrees Celsius, the temperature required to forge the slugs. The slugs are brought to the same temperature in an oven. The punch applies 2,000 tons of pressure to form it into the initial shape of the piston. About 1 in 10 forgings are dunked in water to check for defects. To make forging easier, they pre-lubricate the slugs before heating them. That's why the slug flames up when struck by the press. It only takes 2 seconds for the press to do its job. But the forgings are so hot, they need at least an hour to cool before the next step. Workers heat the forgings twice more. The first time at a very high heat to strengthen the metal. The second time at a lower heat to stabilize it. Now, they insert each slug in a lathe to give the forging the correct shape for machines that handle it later. These small holes allow oil to flow through to lubricate the piston when it's in use. Another lathe reduces the diameter by 3 millimeters. The same machine then cuts 3 grooves, 2 for compression rings and another for an oil control ring. These rings help the piston glide and enable it to provide an airtight seal. This hole is for the wrist pin, which will attach the piston to the connecting rod. A milling machine then shaves off up to 2 centimeters of metal from 2 sides of the piston to reduce the overall weight. The white liquid is lubricant to cool the area during cutting. Another milling machine cuts away part of what they call the dome. This way, it'll clear other parts when moving inside the cylinder. The piston must be just the right shape and size. Some of them move up and down as much as 6,000 times per minute when the engine is running. Next, a lathe shaves a hair width more of the metal from the outside. This cut enables the piston to expand slightly when the heat builds up inside the cylinder. An automated drill makes 2 intersecting oil drain holes to enhance lubrication of the wrist pin. Another machine now engraves model and production data. Here, a worker removes sharp edges created during previous operations. He then uses a belt sander to further smooth out the surface. Sharp edges could damage the cylinder walls. This cutting machine shaves off a bit of metal inside the pinhole, so the wrist pin will fit snugly inside. Once the cutting's complete, high-pressure jets spray the pistons with hot deionized water. This cleaning removes all traces of lubricant and oil. And after a blow-dry with an air gun, these pistons are ready to go through their ups and downs. Norman Breakey, a Canadian, invented the paint roller in 1940. It revolutionized painting, but Breakey never got rich because he lacked the financial means to defend his patent. Alongside the brush, the paint roller, with its replaceable cylindrical refill, has become the primary painting tool. The refill is a tube covered in fabric made from either polyester fibre or lint-free acrylic and nylon fibre. Regardless of fabric, all refills are made the same way. The fabric is processed into a 7.3 centimetre wide strip. It goes into a machine called an automatic tube winder. It first applies epoxy glue to the surface of PVC plastic tubes. As a tension bar pulls the fabric strip taut, the machine winds the fabric around a tube. An air jet pushes aside the wound fabric to avoid bumps as more is applied. Once the tube is covered with fabric, the machine simultaneously wraps the end and the start of the next tube in masking tape. Once the glue is dried for 8 hours, the tubes enter a machine that cuts them into several refills. The tube spins as it passes, so one small cut is enough to sever it. One tube produces 9 19-centimetre long refills or 7 24-centimetre long refills, the two standard sizes on the market. The next machine first runs a wire brush against the fabric. This lifts and fluffs the pile. Then a beveled edge is made on each end. To fluff the fabric further, it's spun at 3,500 RPM. During all these operations, a vacuum sucks away loose fibres. Meanwhile, the paint roller handles take shape. An injection moulding machine shoots molten plastic into handle-shaped cavities. A built-in cooling system hardens the plastic within seconds. The handles are made of polypropylene, a tough thermoplastic, and some coloured polyethylene, a lightweight thermoplastic. Now that the handles and refills are made, it's just a matter of assembling them. These plastic bearings hold the components together. The assembly is entirely automated. The bottom bearing goes on first. It rests against the part called the shoulder. Next, the refill. The bottom bearing slots right into the open end of the tube. Now the top bearing goes on. A metal clip locks the bearings and roller in place. And voila! A 7.6 centimetre roller for painting windows and trims. This factory also makes disposable plastic paint trays and tray liners. They're made of polyethylene terephthalate, PET for short, a type of plastic that's strong yet flexible. This thermoform machine heats a PET sheet, then vacuums it into a tray-shaped mould. Fans cool and harden the plastic. This cycle takes less than a minute. The moulded sheets go into a cutter. It removes the trays in one slice. The factory grinds up the leftover plastic and sends it back to the supplier for recycling. This factory also makes roller refills for applying solvents. Paint rollers, spreading happiness and paint wherever they go. Coming up on How It's Made, parachutes. Don't jump till you've seen this one. And chimneys. Stacks of them. See you after the break. Welcome back to How It's Made. When aeroplanes first took off, so did parachutes as the best form of escape. Today's aerodynamic lightweight chutes enable cargo and people to descend safely and land right on target. Let's drop into the factory to see how they're made. This company makes military parachutes. Each one has a 9-meter wingspan and carries up to 200 kilograms. Making the chute's canopy starts with a rugged woven nylon fabric with nylon ribbing. This light table lets a worker detect any flaws in the fabric. The alignment between the ribbing must be consistent. They test the fabric by pulling the material until it rips. To pass, the fabric must withstand a minimum of 20 kilos of pulling force. A laser cuts out the parachute parts, 30 to 100 of them, depending on the model. A vacuum system stabilizes the fabric by sucking it to the table during cutting. The fabric is usually silver-colored to blend in against the daytime sky. A seamstress now sews on nylon tape to attach the parts and reinforce the seams. Some panels have holes about the size of a dinner plate to funnel air between the two layers of the canopy and keep it rigid during flight. Once they've finished sewing, workers inspect the stitching. Every 2.5 centimeters of stitching must have between 7 and 10 stitches. If the stitching is too close or too far apart, the fabric could rip. And that's the last thing you want when your chute is descending at a rate of up to 4 meters per second. So they mark any problem spots with a red ribbon and re-sew them. Here, a worker sews nylon tape to reinforce an area called a flare, which is a triangular patch of nylon reinforced with silicone coating. She loops the tape at one end of the flare's points to later insert what's called a suspension line. The 60 lines link the 60 flares on the canopy to the jumper's harness. To reinforce each flare, she sews 42 zigzag stitches in a 2.5 centimeter area. The nylon suspension line arrives on spools, so workers use this machine to stretch it straight. A worker marks off up to 4.5 meters per line and cuts it on an angle to reduce fraying. Workers later sew the ends into loops so they can attach each one to the loop on the flares. A worker makes a lark's head knot in each line and ties it to a flare. This type of knot is easy to undo if a line needs replacing. Connecting the 60 lines to the canopy's 60 flares takes about 2 hours. Only after all these knots are secure can they pack the chute into the backpack and ship it to the customer. The nylon backpack has two identical parachutes, the main chute and a reserve. This worker is sewing the panels that'll encase the reserve chute. Extra stitching reinforces the straps. Strict guidelines must be followed when packing the chute. The ends must be rolled, then the rest folded into layers. Before each jump, the lines must be untangled and checked for any tears from the previous jump. The lines and the canopy are inserted into the pack. Pulling on this red handle deploys the main chute. The yellow handle is for the reserve chute. There are straps over the shoulders, chest, belly and legs. Finally, 3 buckles attach the harness to the jumper. Good luck! Chimneys vent hot gases or smoke from your fireplace to the outside. Some types also channel air to the fire to keep it burning. Although the concept's very old, today's chimneys have come a long way, and making them is an exhausting business. This company makes chimneys for gas-fired and wood-burning fireplaces. A chimney's inner chamber is called a flue. For a wood-burning fireplace, they make the flue from stainless steel. Workers unwind a sheet, then slice it to the size of the flue section they're making. The sections are up to 25 centimetres wide and 1.2 metres long. They assemble as many as they need to make a complete chimney. Here, a worker folds the edges in opposite directions, which will enable them to interlock. Rollers then curl the sheet into a cylinder. The metal's only about as thick as 4 pieces of paper stacked together. This keeps the chimney lightweight. They weld together the top and bottom ends, and a roller flattens the welded seam. They insert the bottom of the flue between 2 rollers. They form a ridge to which a coupler will later attach. They crimp the metal at the top so it can also hold a coupler. To make top-end couplers, a die punches the shape from lubricated sheets of stainless steel. A robotic arm then suctions out the coupler and places it into another machine that cuts threads into the sides of it. These threads enable the chimney sections to twist and lock together. To attach the coupler, a worker mounts it on top of the flue. A roller then pushes against the flue and the coupler. This expands the metal and secures the pieces together. Now, to join the flue with the outer casing, an 8-sided die pushes out against the coupler to attach it to the flue and the casing. They insulate the chimney with shredded ceramic fibre that can withstand a temperature of over 1,000 degrees Celsius. Workers feed the fibre into a machine that packs it into the cavity between the flue and the casing. The machine then moves the chimney to another station, where it twists a coupler to the bottom end to close the cavity. After a quick brushing to remove any fibre dust, a mechanical arm lifts the chimney and moves it to be boxed and shipped. A gas-burning fireplace generates less heat and fewer corrosive gases, so the chimney flue is made of aluminium-coated steel and the casing of a zinc aluminium alloy. More affordable materials, yet still well above safety standards. The airspace between the flue and the casing provides the required insulation. A worker places the flue inside an automated welder. It fuses the edges with a laser that's as thin as a human hair. This is called a butt laser weld, because the machine butts the edges together and bonds them. Next, an 8-sided die indents the section with 3 ridges. A component will fit into these indentations later. Here, a machine creates a star-shaped component called a spacer. They use 2 of them to center the flue in the casing. A worker installs a spacer at each end of the flue. Then he inserts the flue into the casing and twists it to lock the spacers into ridges. This connects and aligns the chimney sections. The tops of the chimneys have steel rain caps. They let smoke and gases vent but keep the rain out, ensuring that where there's smoke, there is indeed still fire. So, whether you're the type who likes to tinker with your engine, or maybe you're a DIY devotee, or a person who prefers to plummet from the sky, now you know how it's made. Today on How It's Made. CO2 cartridges, propellants that work well under pressure. Pretzels, a twisted tail. Scissor lifts, taking workers to new heights. And skating rinks will glide you through this one. But first, paintballing helps you blow off a little steam. The force of the carbon dioxide being released from cartridges propels the ammunition towards its target. The cartridges are also used for inflating things like bike tires and life preservers. This factory works well under pressure. A CO2 cartridge packs a lot of punch into a little package. This one can propel dozens of shots. To make one, they unroll some steel and straighten it out. Then, a punch press descends with 110 tons of force, cutting the steel into discs. Simultaneously, a machine moves up from below to shape the discs into cups. The cups move down a vibrating lane. They're delivered to a series of cylindrical punches, each one with a smaller diameter than the last. Each successive punch lengthens and narrows the cups, as nozzles flush them with lubricant. The process is called redrawing, and at the end of it, the cups look more like test tubes. In just a few minutes, the steel has undergone several transformations. To continue shaping the tubes, they heat the ends by dropping them through an induction coil. Intense magnetic fields excite the molecules in the metal, causing it to heat up rapidly. This machine is called a necker. As it revolves, it delivers the tubes to a series of dies that pinch their ends. With each pinch, the ends get progressively smaller. This creates necks in the tubes. As the diameter of the neck narrows, the tube takes the shape of a bottle. Now, Each cartridge goes on a lathe. A cutting tool plunge cuts the neck to shorten it. Then it carves out a lip. The cartridges now head through a washing station, where soap and water get rid of the oily lubricant. A trip under some gas burners dries them off, and they head to the filling station. Here there's a tank full of carbon dioxide. The filling head pumps liquid CO2 into the cartridges and then caps them. The gaseous form of CO2 in the cartridges is under great pressure. Releasing even just a little through a gun will be enough to propel things like pellets and paintballs. They do spot checks to make sure the cartridges are tightly sealed. Now it's on to the next station, where they'll be made to look shiny and new. The cartridges are inside this revolving drum, which delivers an electrical charge, attracting zinc from the tank to plate the cartridges. The smooth zinc plating doesn't just look good, it's a better surface to print information on. At this rotary silk screening station, the brand name and cautionary information are printed onto the sides of the cartridges. A quick bake under an ultraviolet light cures the ink. And these CO2 cartridges are now ready to demonstrate the power of compression. Be sure that's a paintball gun. Always check, and don't do this at home, kids. How and when the first pretzel came to be depends on who you ask. One story tells of a monk baking rewards for children who were pious. Today's bakeries still fold the dough to resemble arms crossed in prayer, but they do it much faster, granting tasty wishes to a lot more snackers. Although hard pretzels are more common, this company makes the more traditional soft-bake ones. To make enough dough for 5,000 pretzels, a worker first blends shortening, sugar and salt in a huge mixer. The machine automatically adds yeast, corn syrup, 6,200 litres of cold water and 345 kilos of flour. The cold water helps make the dough elastic, so workers can shape it before it hardens. A worker then opens the mixer and slows the blades to help the dough fall out. He splits the batch on a table, then creates chunks that go into a tank called a hopper. It feeds an auger that channels the dough chunks through guillotines. The blades chop the chunks into 70-gram balls to make small pretzels or 140-gram balls for large pretzels. Two conveyor belts squeeze them into 40-centimetre-long segments called noodles. Another machine now grabs the ends of each noodle and twists the ends over each other to create the pretzel's 3 signature holes. To keep this knot from unravelling, the plate then gently flips the pretzel dough onto another plate below. That plate carefully flips the doughy creations onto a 36-metre-long conveyor belt. The raw pretzels now travel on the conveyor for 14 minutes, the time it takes for the dough to rise. Next, they move through showers of liquid sodium hydroxide, heated to 82 degrees Celsius. That seals in the moisture, so the pretzel will be chewy when you eat it. They go into a large oven. As they enter, flames sear and harden the outside. This prevents the bottoms from sticking to the mesh conveyor belt during baking. After about 3.5 minutes at 293 degrees Celsius, the pretzels are piping hot and golden brown. They drop onto a long conveyor, where they gradually cool on their way to the next step, a trip through a freezer that's longer than 7 Olympic-sized swimming pools. After 30 minutes at minus 28 degrees Celsius, the pretzels are rock solid and ready for packaging. But first, a camera scans them so that a computer can track each pretzel and guide a robotic arm to pick it up. This arm is one of 5 operating at separate points on the line. The robots process 1 pretzel per second and clean up after each other until the belt is picked clean. The pretzels then fall through a sliding gate, landing on a conveyor that whisks them off to the next step. There, a machine drops a packet of coarse salt into each bin of 6 pretzels. A mechanical arm nudges the pretzels over to make room for it. The salt packet lets you season your pretzel the traditional way before warming it up at home. The machine opens plastic bags with compressed air. Mechanical arms push the pretzels and salt packet inside. A robot arm then places each bag in a cardboard box. So, next time you're looking for a salty snack, don't tie yourself up in knots, just have a pretzel instead. Coming up on How It's Made, scissor lifts. It's uplifting stuff. And skating rinks. We bring you some cool coverage. See you after the break. Welcome back to How It's Made. A scissor lift is a mobile work platform that rises. The elevating mechanism consists of arms that connect in the middle like scissors, hence the name. They're a common sight on construction sites or in big warehouses. How It's Made is on the up. The number of arms in the scissor mechanism varies according to the height of each particular model. The factory constructs the scissor arms from steel tubes. The first step is to cut them to the right length for the model in production. A worker uses an air gun to blow off the tiny shards of metal the cutting leaves behind. The arms go into a press that punches a hole for a hollow steel cylinder called a boss. The boss is the housing for a pin that will connect one arm to the other, yet still allow them to pivot like a pair of scissors. Workers now use a magnetic crane to move the arm to the welding area. They insert the boss into the hole, then tack it in place. This piece will go on the end of each scissor arm, but first, they weld on another boss. Now fully assembled, this piece is called the male scissor end. They tack it to one end of the scissor arm and tack a female scissor end to the arm's other end. Robots now weld the two end pieces simultaneously. then the boss in the middle. Now workers stack the scissor arms, putting a pin in each middle boss. They also install the hydraulic lift cylinder that will raise and lower the scissor stack. This manifold activates the lift cylinder by increasing and decreasing hydraulic pressure. Workers fasten the connected scissor ends to each other by driving a pin through the boss. They secure it with a locking mechanism called a cotter pin. Meanwhile, other workers assemble the base of the scissor lift. At this stage, it's upside down. At the rear, workers bolt in a hydraulic wheel motor. Hydraulic pressure turns the motor, enabling the operator to move the scissor lift forward or backward. They slide a wheel onto a hub and bolt it securely. This is the wheel hub onto which the front wheels bolt. It attaches with a pin, locked by a cotter pin. They install the hydraulic steering cylinder. This steel tie rod links the front wheels to each other, so that they turn together. Now, workers hook up the hydraulic hoses. They pump in grease to lubricate the cylinder. Next, they assemble and install the hydraulic tray. It contains the electrical panel that controls all the machine functions, as well as the hydraulic tank and pump. The pump forces hydraulic fluid to the wheel motor, steering cylinder and lift cylinder. The hydraulic tray swings closed under the base. On the other side, they install 4 6-volt batteries that power the lift. The scissor stack, meanwhile, is in the paint booth getting a coat of primer, then a coat of urethane paint. This finish prevents the steel from rusting. After curing the paint in an oven, they install the scissor stack onto the base. Now they connect the 2 hoses that run between the lift cylinder and the hydraulic pump. Through one hose, fluid goes to the cylinder to raise the scissor. Through the other, fluid withdraws to lower the scissor. They run cables from the electrical panel up through the scissor stack. After installing a platform made of painted steel, they connect the cables to a control box on the platform rail. These controls enable a worker to operate the scissor lift from the platform. After a test drive, it's time to apply the decals. Up to 75 of them, depending on the model. And if you've got more than one, you can go in for a little synchronized scissor lifting. Nice. A regulation ice hockey rink is 61 metres long by 26 metres wide. Making the ice is an art. If the ice is too thick, it'll tax the refrigeration system and soften on top. If it's too thin, the skate blades will cut right through it. This process allows for no slip-ups. The rink floor is a concrete slab. Covering it with ice begins in the arena's refrigeration room. There, a compressor pumps fluid, usually methanol or saline, through pipes running underneath the rink's floor. The concrete chills to around -8 degrees Celsius, the temperature required for water to freeze on concrete. This company made its own ice-making machine by refitting an ice resurfacer. Its onboard water tank feeds 20 sprayers that mist a 4-metre span. The water freezes within seconds. To make a quality ice surface, you have to build up the ice in layers, each about 2 millimetres thick. Driving in the standard outside to inside oval pattern, each layer takes just 8 minutes. With 2 layers down, they paint the ice white. You'd think it would be simpler just to paint directly onto the concrete, but the paint would chip off when they remove the ice at the end of the season. They would have to scrape and clean the slab before repainting it, a messy and expensive job. So instead, the ice maker mixes water and powdered paint in the onboard tank and sprays 3 layers onto the ice. This paint doesn't dry. Just like the water the machine sprayed before, it freezes into white ice. This metal dioxide paint is specially formulated for skating rinks, designed to cling to a base coat of ice. And unlike concrete paint, it's non-toxic and biodegradable, so that at the end of the season, the arena can melt the ice and let the water drain out without contaminating the environment. Now, a crew comes in to paint the hockey markings. Workers lay down string to mark the borders of the red line, the blue lines, and the goal lines. They elevate intersecting lines so that the paintbrush can pass. To paint the face-off circles, workers use an anchor, cable, and what's called a paint stick. This takes just 20 minutes. The paint is in a portable tank. It flows down the paint stick tube to a rectangular pad on the end. For the goal crease at each net, they trace a template. They fill it in with blue. The same technique is used to paint the 8 red face-off spots. Back to the blue line. First, they spray water to freeze the strings in place. Then, using a brush on the same type of paint stick they use for the circles, they fill in the 30-centimeter wide space between the strings. Now for the home team's logo at the center of the ice. After dabbing a mop in blue chalk, they run it over a computer-generated paper stencil of the logo. This transfers the design outline to the ice. They spray water on the chalk lines to freeze them in place, then paint the logo. Finally, with a garden hose, they spray water over all the markings to seal the paint. Then they slowly flood the ice with a larger hose for about a day and a half. This adds the final 3 centimeters of ice. The now skatable ice surface is about 4 centimeters thick, containing some 50,000 liters of water, about 300 bathtubs full. So, whether you enjoy being put under pressure, or fancy a little salted snack, or you're looking to go up in the world, now you know how it's made. Today on How It's Made. Pro hockey sticks. The puck stops here. Bronzed baby shoes. We take you through the process, one step at a time. Treadmills. We'll bring you up to speed about how they make them. And handheld computers. Computer processing unplugged. But first, today's cutting-edge ice hockey sticks are made primarily of graphite, a strong yet lightweight material woven from carbon. Professional hockey players have them custom-made, with the curve and angle of the blade tailored to precise specifications. You'll want to stick around for this one. To construct the stick's hollow shaft, 15 sheets of graphite are layered, each in a different direction to make the shaft uniformly rigid. Heat-activated resin molds the layers together. This machine, called a flex tester, measures how much force it takes to bend the shaft 2.5 centimeters. If the force is within a certain range, the shaft has the correct degree of stiffness for that model. The blade starts with a plastic core. In the center, there's a piece of hard foam wrapped in graphite. It absorbs the impact of the puck. Later, the core will be molded to the shaft, but for now, it's glued and clamped together. When the glue has dried, the core is covered in a graphite sock. The sock's fibers run diagonally. The fibers of subsequent layers run in other directions, building a combination of crisscrossed fibers that creates uniform stiffness throughout the blade. Now the core goes into a glue applicator. This heat-activated plastic resin permeates the graphite. Once it cures, it will fortify the material. On the next 2 layers of graphite are strips. On one, the fibers run vertically. On the other, they run diagonally. They're stiffer because they've already had a resin application. They run through the glue applicator and go onto the core. This is how the factory builds its graphite blades, whether mass-producing amateur sticks or making a few special order sticks for a professional player. At this point, retail sticks head into large-scale automated production. The professional sticks continue to be made by hand. Initially, a customized wooden mold is produced for each player's stick, and it's given an identification number to prevent mix-ups. This 2-piece mold is installed on a press. The press shapes the blade to the player's precise specifications for the face, or vertical angle, and the curve. This molding process also compresses the graphite layers into a single unit and permanently bonds the blade to the shaft. The plastic bag over the blade prevents excess resin from oozing over the press. With a router, the blade is profiled to a specific shape. Each player orders his own personal template. It can be any shape, as long as it abides by the Hockey League's regulations. Maximum curve, 19 millimeters. Maximum height, 7.6 centimeters. Maximum length, 30 centimeters. Now the blade gets a good sanding and a thorough buffing. The blades are dipped in urethane, a colourless coating that fills in tiny imperfections on the surface. Once that dries, a machine sprays silver paint at the base of the shaft. Finally, another coat of urethane to seal and protect the paint. For the retail market, this company mass produces 6 models of graphite hockey sticks in a right-handed and left-handed version. They all have the same blade shape, but different curves. You can peel off the removable model name and write your own name on the shaft instead. It's not nearly as personalised as a made-to-order model, but at least you won't go home with somebody else's hockey stick by mistake. The pitter-patter of little footsteps is a welcome sound in any household. But before you know it, children have grown up. Bronzing baby shoes is one way to preserve the memory of those early years. The tradition was started back in the 1930s. We look at the process step by step. In these shoes, a child learned to stand on his own 2 feet. His baby shoes have joined piles of others. They're about to be preserved forever. Information about the shoe's owners is recorded, including personal details for engraving. A tracking number is assigned to each pair. Without it, some shoes might not find their way back to their owners. That number is stamped onto insoles. There's a special coating on the insoles that will prevent the metal plating from sticking to them, so this number will be visible throughout processing. The insoles are stapled down. And then the shoes are dipped in a special formula. It chemically seals them and will also help stiffen them as they dry later. But first they're hung to allow excess liquid to drip off. Each shoe is stuffed with plastic to give it shape. A rolled plastic form is pushed into each shoe to complete the shaping. The laces are tied and the bows are positioned flat against the shoes, so they won't break off during the rest of the process. As an extra precaution, a rubber band is wrapped around each bow and then glued down. With the shaping plastic removed and the shoes dried and stiffened, holes are drilled into the bottom of the soles. This will allow them to be hung on prongs later during plating. But before that happens, a mix of water, copper and other ingredients is stirred. A rack full of baby shoes is carefully submerged into the coppery liquid. This isn't the final coating, it's a key preparation step. It makes the shoes conductive so they can be electroplated. The shoes are hung to dry, and a little more of the liquid is dribbled onto them to cover any bare spots. The finish is allowed to dry for a couple of days. Then, they're lowered into the electroplating tank. An electrical current runs through to the shoes, attracting copper in the tank to plate them. Using a special polishing wheel, the bright copper finish is scratched. This prepares them for the next step. A black finish is sprayed onto the shoes. And then it's wiped off, rubbing some into the crevices to give them an antique appearance. Next, they're sprayed with a protective lacquer. You can still see the identification number clearly on the insole, so they haven't lost track of the owner. The engraving plate is attached onto a wooden base, and the shoes are screwed onto it. Now they won't be going anywhere, except down memory lane. And it seems there's no end of bronzed keepsakes that can also take you there. From cowboy boots to burgers on a bun. I remember that one. Coming up on how it's made. Treadmills. To make them is no walk in the park. and handheld computers, high-tech gadgetry that fits in the palm of your hand. See you after the break. Welcome back to How It's Made. Treadmills were invented back in the 1800s. Farmers put animals on treadmills to power butter churns and threshing machines. It wasn't until the middle of the 20th century that people started working out on treadmills. And as a fitness concept, it's been a runaway success. In these high-tech treadmills, computer processors assess your level of fitness and plot your workout program. To make one, they punch holes in aluminium frame side pieces. These holes will be used to attach other parts. But first, they weld joints to the side pieces. And they weld brackets onto the platform that will hold the treadmill's motor. They position the platform between two aluminium side pieces and screw it into place to complete the frame. Next, they attach the elevation mechanism. This piece will raise the treadmill belt. They fasten wheels to the frame that will allow the treadmill to be rolled away for storage. They turn over the treadmill frame and work on the underside. They attach brackets for the rollers that go inside the belt. Then they position the belt and deck over the frame. They slide in steel rollers and attach the drive belt. They bolt a large shock absorber to the drive motor to dampen its vibration. They install a strobe disc and then place an optical sensor over it. With the help of this sensor, the strobe will monitor the motor speed 16 times per second. They mount the drive motor for the treadmill belt on a special platform and bolt it into place. At this point, they attach one of the computer boards. It receives information from the optical sensor about the treadmill's speed and relays it to the computer in the control panel. This will ensure that everything is in sync. Here, they slide a protective casing over the framework. They cap the ends, then turn over the machine once more to install the mechanism that allows the treadmill to be folded up when the workout is over. They screw a plastic cover onto it to protect the bottom. And it's over to the control system. They stick the control membrane onto the plastic housing and attach a safety switch to the back. Then they install the treadmill's other computer board in this housing. They plug a wire into the safety switch and install a receiver to pick up the runner's heart rate. They secure the handlebar assembly to the control housing and plug in the upper circuit board. Now they close the back of the control system and it's time for the two assemblies to come together. They connect the upper and lower computer boards so they can communicate. And then they give the treadmill a little test run to make sure it's on top form. They put it through a range of elevations and check the belt to determine if it's running in the middle. They adjust the belt to center it a little better. The treadmill has passed inspection. So they wipe away their footprints and press the brand label onto the hood. They lower the hood onto the motor. And now this treadmill is ready to give you a good run for your money. Go on, faster. Handhelds are rugged computers designed for workers on the move. They're used by delivery drivers, policemen, and in warehouses. They process data in virtually any condition, from bad weather to rough roads. So even though you're in the field, you're still plugged in. From scanning barcodes to reading parking meters, handhelds provide information on location. They start with the keyboard electronics panel. They test each contact for conductivity. Then, they transfer the tracking number from the electronics panel to the inner casing, so it will be visible if it needs servicing. They glue the panel to the casing with silicone for a waterproof seal. The rubber keypad goes on next. Then, they glue a protective plastic plate over it. Next, they cut a silicone liner to the size of the computer screen. It will help seal the unit, preventing water and dust from getting in. They place the liner in a bracket behind the screen, and then use this jig to align the screen to the computer casing. A dab of thread locker glue to the screws helps to hold it all together. The top casing for this handheld computer is now assembled. They move onto the back casing and install a speaker. They apply a layer of silicone to a circuit board assembly, again to resist water and dust. This circuit board assembly goes into a hole in the back casing. It will allow the unit to communicate with a central computer. In the next step, they wire the speakers to the circuit board, and now the handheld has a sound system. More silicone on these connections. Then they install triggers for the scanner, one on each side. They install a liner on the door for the memory card compartment. Then they run the top assemblies for 3 hours in extreme temperatures. Once the inner workings have been completely installed, they attach the top assemblies to the bottom ones. They tuck the battery pack into its compartment and install the end cap. It has an antenna for wireless communication. Now, they install a smart card reader because this particular handheld computer will be used for security checks on personal ID cards. They test the laser scanner, then activate security software, which reads fingerprints, allowing this handheld computer to do security or criminal checks on the spot. When an unregistered person presses a finger onto the print reader, this is what happens. Of course, mobile computers are designed to return to a home base, where they upload information into the main computer. But first, randomly selected units get roughed up in a series of tests. They toss this unit into a tumbler, and it gets thrown around. Then they drop it from a height of 2 meters. They plunge it into a tank of water. In the real world, things can be even tougher. This computer ended up in a fire. And this one was run over. But even when it seems they've been completely destroyed, information can still be salvaged. Here they transfer the memory board from one of the wrecked units to an undamaged one. They hook it up to the central computer and retrieve the information. After all, these units are really all about the facts. So, whether you want to be a hit with your teammates, or want to walk down memory lane, or simply walk from A to A, now you know how it's made. Today on How It's Made. Motorcycles. We'll take you to the factory where production goes in cycles. Clay pipes. Making them is an underground business. Drumsticks. We could bang on about this forever. And whistles. A thrilling story that'll blow you away. But first, the invention of the motorcycle in the late 19th century was speed-driven. People wanted to go places faster than they could on a bicycle, so they strapped an engine on a bike. A simple concept. Today's motorbikes are far more complex, and they leave the earlier versions in the dust. These motorbikes are an engineering feat. They start by welding the frame out of lightweight aluminium, an advantage for speed and fuel efficiency. The frames are cleaned, powder painted, then baked to cure the paint. They fit a crankshaft and pistons into the engine's left block. They tighten the bearings and caps, then slide in a U-shaped tool called a fork that orientates the pistons in an upright position. Next, they compress the piston rings with another tool so that the pistons easily slide into place as they install the other half of the engine block. They place a gasket on the top of the block and then install the cylinder head. Using torque-controlled electric tools, they tighten the bolts to attach the cylinder head to the block assembly. They install the camshaft in the cylinder head unit. The camshaft will drive the valves that bring in air and fuel and let out the exhaust. They rotate the crankshaft to fine-tune its action. Now it's time to give this engine a test run. They fill the engine with coolant, lubricant and fuel, then run through the gears. They check for leaks and overall function. When it passes inspection, they purge the coolant from the engine. A motorbike engine isn't only about function, it also has to look good, because it won't be totally hidden under a bonnet. Now, they lower the 102-kilogram engine onto a cradle that sits on a conveyor. They mount the frame onto it. They attach the rear wheel assembly, and then the front. They attach the handlebar using the correct amount of torque. and they tighten the brake assemblies. Next, they fill the radiator with antifreeze. Meanwhile, over in the paint department, robots are hard at work. They attach the painted pieces to the bike. First the saddlebag body, then the lid, and finally the trunk body. Then they assemble the instrumentation, such as the speedometer and fuel gauges. This part is called the front cowl, and it goes in front of the instrumentation. They lower the front cowl with the meter panel onto the bike. And then they bolt everything to the frame. Finally, they install a cover for the exhaust pipe. They check everything to make sure it's solidly put together. Then they pull up to a dynamometer, a machine that measures mechanical power. They check the bike's speed, brakes, horn, navigation system, and the cruise control. Every motorbike undergoes this scrutiny, and if it passes, it's ready for life on the open road. Clay pipes are part of a major underground network, one that's dedicated to proper drainage. We flush without thinking, but it may surprise you to learn that clay pipes have been serving us well for thousands of years, ever since the days of ancient Babylonia. They're the sanitary sewer system's oldest secret. These pipes can take a lot of stress. They bear the weight of soil and structures overhead, and they won't corrode. They start with scrap clay from manufacturing, raw clay, and shale. After these materials have been roughly processed, a loader scoops the mix onto a conveyor that takes it to a mill for a finer grading. At this point, the mix has about 10% natural moisture, but it's not enough for it to stick together. So they add more water as it falls into a mixer. The mixer evenly distributes the water in the mix, then moves it towards an extruder that pushes the clay through a pipe-shaped die. The clay pipe that emerges is 20 centimeters in diameter, the size that typically serves a residential side street. It has a bell-shaped opening. It's the female part of the joint that will fit into the male end of another pipe. A rotating blade trims away the ragged edges. Then, an automated system loads several pipes at a time onto a rack to await the next step. Over on another production line, they're making flue liners for chimneys. The clay is fairly soft at this point, so lettering wheels can easily engrave information. And they cut it to size, using thin wire. An upender stacks it on a pallet to await further processing. Elsewhere in the plant, a main trunk sewer pipe is born. With a diameter of over 38 centimeters, it's big and needs a substantial trim job to get rid of the rough edges. It weighs well over 300 kilograms, nearly 5 times that of the residential pipe. Once they're fabricated, every clay pipe goes into a dryer for at least 24 hours. A trip through a kiln will toughen them up even more. They'll spend about 50 hours in here, exposed to very high temperatures. This is called vitrification. It fuses the mineral particles together. They tap each pipe with a hammer to test if it's solid and perform a thorough visual inspection. To join lengths of pipe together, they pour polyester resin into the female joint molds that have been placed in the bell-shaped pipes. The resin hardens, forming an O-ring, and the primer brushed on earlier helps the new resin joint adhere to the clay pipe. Next, they make a male joint by pouring resin around its spigot end. This will make for a joint with a tight seal. They test the joints by pumping water into the pipe. Then they raise it and place a load on the joint. This joint will withstand over a metric ton of pressure, which more than meets industry requirements. Now, they do another type of test on a basic clay pipe. A hydraulic jack applies pressure on the pipe. The number on the gauge far exceeds the burden of being buried underground. And so these pipes are now ready for civic duty, down in the sewers. Coming up on how it's made, drumsticks. We're on a roll with this one. And whistles, for all you referees and ravers out there. See you after the break. Drumsticks are designed for a life of hard knocks. They're usually made of hickory, which is heavier and sturdier than other woods. Hickory can also absorb a lot of shock, which means a drumstick made from it is easier on the hands and wrists, so the drummer doesn't have to suffer for his music. Hickory drumsticks also have good balance and feel, so it's easier to hit the right note. To make them, automated arms serve up hickory dowels to a 3-bladed cutting device that moves on a rail. As the blades shape the spinning dowels, they form a round tip, a narrow shoulder, and a shaft that gradually widens. They spray each stick with a protective coating. These round blades remove the stubs, the ends where the sticks were held during the initial machining. It's just a rough trim, and the ends need more work. So they feed them to spinning chucks with blades. The chucks are inside protective metal housing because they spin very fast and the blades are extremely sharp. For a demonstration, the housing on one of the chucks has been removed and they turn it by hand. The chuck usually rotates at 10,000 RPM, but at this slow speed you can see just how it shaves an end into the desired shape. The stick comes out of the chuck with a nicely rounded tip. Now, they test the sticks. Each one rolls down steel rails that have been specially aligned. If it rolls straight, it means the stick is straight, but if it wobbles, it isn't and will be impossible to play with. They reject those sticks. Next, a printer embosses the brand name and model number onto each of the drumsticks. They sort each drumstick by weight. Even if two sticks have been made exactly the same shape and size, their weight can vary because wood has different densities, and that's something that affects the stick's feel and tone. For example, this drumstick weighs 53 grams, but the next one comes in at 55. Over at another workstation, they're making a different kind of drumstick, a felt-tip mallet that will have a softer sound. They press a wooden shaft into the glue-filled hole of the felt ball. The hole is a bit smaller than the shaft, resulting in a tight bond between the stick and the felt head. They do a sound check on the other sticks. Even though they've been sorted by weight, there are still subtle differences in tone. A computer analyzes their sound and matches pairs. It's a bit like a dating game. The unmated sticks go back into the mix, and then they try to match them up again. This matching process is critical. If one stick has a different pitch, the sound will be off balance. They assign a numerical value to each pair of drumsticks. A cardboard sleeve holds each matched pair together. From a rough wooden dowel to a sleek drumstick, a process that's designed for impact. When you blow into a whistle, part of the airstream exits the slot in a swirling motion, generating sound. The rest of the airstream travels through the whistle chamber, then exits the slot, reinforcing the sound. And if you've ever wondered why it's in there, the little ball inside puts the trill in the whistle blast. Production begins with a narrow brass sheet, not quite a millimetre thick. A punch press slices through the sheet, cutting a square connected to two circles. The factory calls these pieces the Mickey Mouse ears. I wonder why. One by one, they go into a second press that folds the circles inward to form the sides of the whistle's barrel, and bends the edges of the square inward to form the top and sides of the mouthpiece. At the same time, it strikes the mouthpiece against a die that embosses the company logo into the metal. Another brass sheet feeds a third press. This machine punches out and partially shapes the part that forms the rest of the whistle. It notches the tapered end, which will be the underside of the mouthpiece, giving your teeth something to grip. Now a fourth press finishes shaping these pieces. It bends the other end into a circle to form the barrel. The two main parts of the whistle are now ready. A worker snaps them together with pliers. Note on the bottom piece, the barrel stops short of meeting the top of the mouthpiece. This creates the whistle's air slot. This press cuts and folds a brass sheet into the third and final part of the whistle, called the tip. It's a piece on the back that holds a ring for hanging the whistle. The tips go into a bowl feeder. The vibration orientates them into the same direction, so that a robotic arm can pick them up and put them in a holder. Tin and silver solder is applied to each tip. This will bond it to the whistle. To fuse all the parts together, solder is applied in 6 different spots. The solder liquefies as a gas flame heats it to 600 degrees Celsius. It flows around all the seams, filling them in a matter of seconds. A blast of cold air solidifies the solder. Even then, it's still steaming as the whistle comes off the machine. The ball that goes inside the barrel is about 1 centimetre in diameter and made of synthetic cork, which doesn't absorb moisture, so the ball never gets soggy and stuck. A worker holds each whistle, now plated with nickel, against the insertion machine. The device works like these pliers, squeezing a ball through the whistle's air slot. With one side of the barrel cut away, you can see how the ball regains its shape as soon as it clears the slot. The last step is to hook a steel ring onto each tip. The factory packages its whistles with a nylon cord, called a lanyard. A hook on one end attaches it to the whistle's ring. Another accessory in the package is a rubber cover for the mouthpiece. It makes holding the whistle in your mouth for a long time more comfortable. This factory also makes customized whistles. You can order them with your own logo. Or to really blow someone away, you can present them with a 24-carat gold-plated award whistle. So, whether you want to get out on the highway, or you're interested in how the waste gets washed away, or you like to spend your time banging away, now you know how it's made. Today on How It's Made. Handcuffs. Making them is a turnkey operation. Corking and joint compound. We'll fill you in. Propane tanks. Containers that allow you to cook with gas. And forensic facial reconstruction. Putting a face on a mystery case. But first, the need for restraint goes back centuries. Handcuffs were originally a loose device until 1862, when adjustable ratchets were added. They allow the cuffs to snugly grip the suspect's wrists. When a crime is committed, a slap on the wrists usually isn't enough. It's time to handcuff them. When they put the handcuffs on, you know you're in a tight situation. Handcuffs start with a roll of steel. A machine pulls it through a straightener and then through a die that punches out a handcuff frame part. A revolving barrel cage sifts out the waste and kicks the frames into a bin. Here, a worker stacks U-shaped steel parts on a fixture, which he then clamps into a machine. A cutter makes ratchet teeth in the parts. Coolant keeps the tool from heating up and getting too soft to do the job. Each set of handcuffs will have 2 of these ratchets. Next, they load steel rods into a slowly revolving device. It moves the rods through a series of cutters. This is how they make swivels for the handcuffs. They round the tips of the rods and then carve necks below. This tool slices the swivel to the proper length. And then the partially finished swivel falls into a basket. Next, a drill works on the rounded tip, scooping out the center. And now you have a finished swivel. They take 2 chain links and 2 swivels. They make a small chain, 2 links with swivels on the ends. They lock the links and the swivels together. And now the swivel link assembly is complete. The swivels will provide some rotational freedom between the cuffs. If they don't weld the links together, the prisoner could have total freedom. It's time to assemble the handcuffs. They install studs in the outer framework and attach the ratchets to them. The swivel link fits into the little grooves in the framework. They hammer the inner frame on and then fit the top and bottom assemblies together. A tap with the hammer holds them loosely together. Then a press bears down to make a tight seal. These cuffs look complete, but they aren't quite ready for a life of crime. They need to be toughened up. So they spend 25 minutes in a furnace, and the searing heat hardens the steel. This is the pawl, a spring-loaded bar that will engage the teeth of the ratchet. They lock the pawl and spring in place. A press pushes pins into the assembly to hold everything in position. Then they stamp serial numbers onto each set of handcuffs so that the police can keep track of them. Now the handcuffs shake in a vibrating bin full of stones. This polishes the rough edges. It's time for the ultimate test. They activate a 500-pound pull. That's 228 kilograms in metric. And the handcuffs remain strong. They also tap each set to make sure the ratchets drop freely. Handcuffs are temporary restraints, and most can be opened with a universal key. They pack 2 with each set, along with the instructions. There's no doubt they'll have a captive market, because there's always someone who needs to be locked up. But then again, there are also those who deserve their freedom. The need to seal windows and cracks in walls and floors has been around since antiquity. Lucky for us, we no longer have to stuff rags or smelly fish glue into these crevices. Today's caulking and drywall compounds form durable synthetic seals that also blend into the decor. This company's caulking comes in 2 types, latex and acrylic. Both good for indoor and outdoor use. To make acrylic caulking, they blend water with chemicals that prevent mold and help the caulking withstand cold weather. Everything blends for about 1 minute. The batch then goes into another mixer containing 700 kilos of synthetic resin. They add a plasticizer that keeps the caulking flexible over time. A combination of colorants tints the corking, in this case a shade of brown called sandalwood. After 15 minutes of blending, the corking is ready. To test the batch, they cure a sample at 25 degrees Celsius for 1 week, then check its flexibility. If the batch gets the OK, it goes into this machine, which lines up plastic corking tubes. Piston pumps lift 4 tubes at a time, and the nozzles fill each tube with 300 millilitres of corking. The machine can fill up to 1,000 tubes every hour. The machine then seals the bottom end of the tubes with plastic covers. The top ends have closed nozzles with replaceable caps. Thanks to the resins and plasticizers, this company's products can last up to 30 years. That's the tough side of corking, but there's also a gentler, craftier side. Start by drawing a pattern on a piece of paper, then lay glass on top and run corking along the pattern. After 48 hours, the corking hardens into a delicate lattice. Then fill in the spaces with clear silicone for a frosted look. Use a small steel brush and rubber gloves to spread it and create texture. Perfect for a door or bathroom window. This factory also makes joint compound. You use this product to cover cracks, holes and seams in dry wall. To make it, they mix 700 litres of water with chemicals that prevent mould, and a type of clay that makes the compound more spreadable. Now time for the main ingredient, 2,000 kilos of chalk. It's what remains on the wall when the compound dries. Next, they add mica, a mineral whose tiny plates slide over each other to make the compound flexible and help prevent cracking. They test the thickness with a device that gauges how much pressure it takes to stir the compound. Next, they take a sample from every batch and measure the pH level. It should have a reading of 8.8, quite high because of the chalk. This is what's called a sandability test. Technicians first let a precise amount of compound harden on a piece of dry wall. This machine then sands it down, applying 100 strokes in 2 minutes. Technicians then remeasure the combined weight of the compound and dry wall, registering how much has been lost. Maximum weight loss should be 4%. If the batch passes the test, they feed it to this machine. It pumps compound into either small size 3 kilo or large size 7 kilo plastic buckets. Then, using a hydraulic press, a worker seals the containers with plastic covers. To open the bucket, you break a small plastic tab and lift the cover. Joint compound also has its crafty uses. With a stencil, you can apply small amounts in intricate patterns to decorate a picture frame or mirror. Now that is some fancy filler. Coming up on How It's Made. Propane tanks. This one's a real gas. And forensic facial reconstruction. A facial with a difference. Looking good. Welcome back to How It's Made. When you compress propane gas, it turns into a liquid. And as a liquid, it's much more compact, which means you can pack it into small containers. Opening the valve converts it back to gas, giving you energy that you can put to good use. Bottling energy means you can always have fuel on hand. To make these tanks, they start with a big coil of steel. A press punches out 3 discs 50 centimeters in diameter in each swoop. A second press clamps the discs as a cylinder-shaped die thrusts upward, transforming it into a shell. Each shell is 1/2 of a barbecue tank. Next, suctioning devices carry the tank shells over to a trimmer, where a blade gives it a neat edge. Workers then insert flanges into pre-punched holes in the top shells. The top and bottom halves of the tanks now move in separate directions. The tops head into an automated welding station where the flanges are fused to them. The weld has to be perfect so it can take the pressure of compressed fuel without exploding. This die simultaneously bends steel strips into rings and punches holes in them. These rings will be used as pedestals, and the holes can be used to mount the tank to a barbecue. Next, a machine welds the rings to the bottoms of the tank shells. The top and bottom tank shells converge. And a pusher device nudges the tops onto the bottoms. They load each freshly assembled tank onto a welding lathe. The lathe turns as an automated welding gun follows the seam precisely, melting and bonding the 2 pieces together. But this processing has hardened the steel. Not a good thing, because these tanks will need to expand and contract to accommodate pressurized fuel. So they temper the tanks in a furnace. They do random tests of the welded seam. They cut out a piece of the tank and grind it on both sides to expose the weld. Then they use a jack to bend the sample right at the seam. If it doesn't split, it passes the test. In another test, they lower a tank into a water-filled drum. They pump water into the tank, causing pressure inside the drum to rise, proving the tank will expand with pressure changes. The tanks then travel down a row of paint guns, which spray them with electrostatically charged powder paint. The tanks journey over 3/4 of a kilometre to an inspection station. Here workers check for contaminants. Then they drop valves into the flanged openings and place the cylinders in a special machine that screws the valves on tightly. In one final test, they submerge air-filled tanks in water. If the water doesn't bubble up, it means the valve isn't leaking. And after all that, these barbecue tanks should be able to take plenty of grilling. When the usual ways of identifying human remains fail and the investigation stalls, police sometimes need a little image building. Using the skull, they recreate the face of the deceased in the hope that it will jog someone's memory. Talk about giving the case a whole new profile. To reconstruct a face, the specialist uses resin to make an exact replica of the unidentified man's cranium. He attaches it to the rest of the skull cast. And now he has an exact copy of the man's skull. Next, he measures rubber pegs to different lengths that are equivalent to the various thicknesses of facial skin. This short one is placed on the forehead, where the skin is thin. Then he installs eyes made of plastic. Those are suction cups protruding from them. They help him to align the eyes. He shines a light into them to confirm that they're looking straight ahead. Next, he cuts out muscle shapes from rolled clay. This piece simulates the area around the mouth. The dead man's muscles have left tension marks on his skull. Those marks, combined with the knowledge of facial anatomy, help to decide where to build up muscle. He makes the face expressionless, because expressions are unique and impossible to extrapolate from a skull. Next, he sculpts muscle around the eyes. There are no clues about the actual shape of the man's eyes, so he gives them a generic look. The skull does divulge the length and width of the nose, as well as the location of the nostrils. Now the specialist builds up the smiling muscles, followed by the fat and salivary gland. He uses different coloured clay so he can see them more clearly. He maps out a location for the ears, but doesn't yet attach them. He shapes the muscles in the neck, working from measurements and photos from the crime scene. Next, he gives the model skin. As he applies this layer of clay, he uses the protruding pegs as thickness guides. And after much sculpting, the model has come to life. But he needs one more clay ear. The skull offers some hints about the ear's size, but not their shape, so he keeps that generic. Now, he sponges the clay to give it some texture, so it looks even more like real skin. Using a digital camera, the artist photographs the model and then downloads the image onto a computer. Using photo editing software, he transfers some hair to the shot of the clay model. He knows from evidence at the crime scene that the man's hair was styled in dreadlocks and that he had a beard. He borrows brows from another photo. He paints in the brows with a stylus. Using the same technique, he gives the image facial hair. And the skull mold and clay model alone takes 12 days to complete. Time well spent, because once the pictures and information are posted on police sites like this one, it may finally help them put a name to this face. So, whether you're a naughty fella caught in the act, or a DIY nut looking to fill a gap, or simply want to sizzle those bangers on a Barbie, now you know how it's made. Today on How It's Made. Fur coats. We have the details all sewn up. Hearses. A deadly serious business. Outdoor lighting fixtures. A feature that should prove illuminating. And golf tees, getting you into the swing of things. But first... Fur coats have been around through thick and thin. They used to be very bulky, but because of new manufacturing techniques, today's garments are much thinner. Whether a posh person's folly or a fashion faux pas, either way, they're sure to keep you warm. Today, fur coats are made for a changing market that values less bulk and more texture. The beaver pelt undergoes multiple transformations until it barely resembles the original. The fur is steamed to fluff it up. Then it's given a static charge to make the hairs stand on end. The pelt then passes through a row of small blades several times. This shears the fur so that the hairs are uniform and the pelt less bulky. But because the downy undercoat is the most insulating part, this fur will still be warm. Grooving is a new technique that involves carving a pattern into the dyed fur. The blades cut a zigzag pattern down the length of the fur, giving the beaver pelt a unique look and feel. Now, the furrier demonstrates a process called letting out. He feeds a pelt into a machine that slices it into diagonal ribbons. He's literally cutting it to shreds. But when this process is complete, they'll have a new and improved fur. The diagonal strips are sewn together, with each one arranged a little lower than the last. A special sewing machine is used. As the operator feeds the strips, he pushes the fur down so it doesn't get caught in the seam and ruin the look. The narrow strips of fur created by this letting out process will run the full length of a coat. It provides a more flowing look than simply sewing whole pelts together. It also makes the fur a little rippled. A process called blocking will correct that. The leather of the pelt is wetted down. Then, to fit the pattern that's been traced onto a board underneath, it's split a little at the end. The fur is then stapled onto the pattern. It's left to dry overnight, and then the original pattern is traced onto the other side of the fur, now smoothed out from the stretching. The position for a pocket is marked on, and the fur is trimmed to the pattern so the dimensions are now exact. Specialized finishers sew a cloth pocket into the split prepared for it. They stitch in the zip and then cut out pieces of silk to line the coat. Before that lining is sewn in, the front edges of the garment are built up by tacking lamb's wool on the inside edging. This will add structure and help the fur hold its form as the lining is put in. Starched cotton tape now goes into the hem of the coat to keep the fur from stretching. Every fur gets these hand-stitched finishing touches. Once the label goes on, this fur coat is ready for a night on the town. Nice, if you like that sort of thing. Hearses are all about luxury, because luxury says dignity and respect. From the plush custom interior to the stretched and streamlined design, it's nothing but the best for our dearly departed. We're all dying to see how they're made. It's the final journey, and the vehicle is custom-made for the occasion. The hearse's construction begins with the Cadillac chassis. It's been built without rear doors, rear windows, back seats, a boot, or rear bumper. It's sliced in two using a reciprocating saw that cuts through metal like butter. The two halves are pulled apart, so there's just less than 80 centimeters between them. Then the frame rails are welded in place to join the two halves. Each new frame rail is encased with a support piece. The framework for a hearse has to be extremely solid because it will carry heavy loads for many years. The base Cadillac also has more structural reinforcements than a regular vehicle, like stronger wheels and suspension. The steel rear cage and roof frame are hoisted onto the car, and the roof is built up with steel rails. The framework for the casket loading door goes on next. Once the rear cage and extensions to the chassis are in position, the panels are mounted, which are made of a blend of fiberglass and space-age materials. Adhesive seals the panels to the steel skeleton. And all the panels are secured in place with screws. This is a made-to-measure job. The panels fit precisely to the welded cage. Meanwhile, over in the press room, a non-stick coating is rolled onto a die. Then a sheet of steel is placed over it. The steel also receives a coat of the non-stick agent. An 850-ton press then pushes the steel into the die to the shape of the door of the funeral coach. The non-stick coating allows the door to be easily removed without being damaged. The door is attached to the back of the hearse, using super strong hinges because they'll have to stand up to a lot of wear. The door is high and wide and opens to an angle of 135 degrees to allow for easy loading of the casket. After the seams in the body are smoothed out and it's given a high gloss paint job, the roof is covered with a foam pad. Vinyl material is placed over it and pulled snugly around the corners. The deck of the hearse is lined with a heavy-duty laminate. Next, the fabric that covers the ceiling of the hearse is put up. The hardware that will allow the casket to easily roll in and out of the coach is mounted. Finally, the custom-built sign is fixed in place. From the lustrous paint job to the lush, curtained interior, the funeral coach has an ethereal look. Appropriate, since it's designed to make an exit that's out of this world. Coming up on How It's Made, outdoor lighting fixtures, making light work of their production. And golf tees. We'll find out what drives this product. See you after the break. Welcome back to How It's Made. Day or night, streetlights light up our lives. Typically standing as high as 8 meters above the pavement, they cast a warm glow in the darkness and continue to provide street decor during the day. And if you're a dog, you're going to get very excited about this one. This fixture, called a luminaire, starts as a technical drawing. To make certain parts of the luminaire, the factory uses a process called sand casting. To create the internal features of the sand mould, workers take a wooden mould for the part and fill it with a mixture made of white sand. They insert a wire into the centre to make an opening. Then inject carbon dioxide into that opening. This causes a chemical reaction that hardens the sand. They remove the white sand piece called the core from the wooden mould. To cast the external parts of the luminaire, workers start with a mould made of aluminium. Inside it, they build another mould made of brown soil. They place a wood block on top and pack down the soil. They do the same on the other half of the mould. Now, with a copper pipe, they make holes in the soil mould, one into which they pour molten aluminium. The other vents air. They spray the inside with compressed air, so no particles will stick to the cast piece. They position the core into the soil mould. Keys in the soil mould help them position it exactly. Then they pour molten aluminium into the mould. Aluminium is an ideal metal for streetlights because it's lightweight, rust-resistant, and it won't stick to the soil mould. After 2 to 5 minutes, they open the metal frame and shatter the mould. They use a drill to remove the white sand piece from the inside of the cast aluminium part. Next, they sand down the part to make it smooth. Automated drills then pierce pilot holes for various hardware. A welder places a bracket in a vise, then welds a decorative tube onto it. Next, he welds an anchor plate onto a pole. The upper part of the pole is welded to a larger bottom part. All the poles, brackets and luminaire parts go into a series of chemical baths to prepare them for painting. The model shown here comes with tempered glass. They installed the lighting system. First, they position the bowl-shaped aluminium piece. Then the lamp socket is mounted, with the electrical components inside the aluminium bowl. Finally, they install a reflector inside the hood to project the light toward the street. They apply labels with product and maintenance information into the fixture's hood. Now they can close up the luminaire and mount it on a pole or bracket. And let there be light. Before golf tees became popular, players would tee up their ball on a mound of sand. The first peg-style tees were invented more than a century ago. But they didn't really catch on until the 1920s, when one company used professional golfers to promote them. That wooden peg you stick in the ground to hold the ball is almost as important as your golf club. You use a tee on the first stroke of each hole to give your drive shot extra distance. Production begins with white birch logs. Just one 20-centimeter diameter log yields close to 3,000 golf tees. The logs go onto what's called a step feeder. This conveyor transports them to a debarking machine. Then a slasher saws the log into shorter lengths. A roller with steel teeth called the thumper roll secures each log to a sharp chain. This holds the log in place as it heads for the saws. 4 saws work their magic, carving the 1.4-meter-long boards into shorter dowel boards, each measuring 46 centimeters. Then a series of chains lays down the dowel boards in a single file on what's called a moulder infeed roll. The moulder's 2 rotating heads transform the rectangular board into round dowels. An outfeed roll drops each dowel onto a belt for several quality control checks. An inspector examines the dowels, removing defective pieces and setting aside dowels that need more cutting. A single inspector sorts close to 19,000 dowels every hour. They go onto racks that hold 8,900 dowels each. Rack after rack now travels into a lathe. A blade whittles the dowel to a preliminary shape. This tool, called a trumpet, moves over the dowel, sculpting the tee's final shape. A blade simultaneously slices the tee from the dowel and forms the cup. The metamorphosis is almost complete. From wooden boards, to dowels, to tees. Next, the tees go for a tumble in a sanding drum. This cascading action has the tees sanding each other's surface until they're smooth. The slots on this machine separate the good tees from the bad ones and screen out the waste. Long nail-like bumps on the machine divide the tees so that only one drops down at a time. The tee fits through only if it's perfectly shaped. The rejects and wood shavings roll across the top and land elsewhere. The good tees land in a big bin called a tote. Golf tees come in various lengths, but your average one is 7 centimeters long and weighs 0.02 grams. So a tote typically holds some 100,000 tees. A tote dumper then dumps 2 totes of teas into a paint drum. Small steel flights inside the drum send the teas cascading. With each turn, they pick up paint. It takes 2 hours and 38 litres of water-based paint to fully coat the teas. Then another 2 hours to dry the paint. A trapdoor releases the teas onto a vibrating conveyor and into a tote. If these teas are to have printing on them, there's still one more step. They get an extra coat of enamel paint to create a smooth surface for the ink. Shiny or matte, plain or printed, the golf tee has come a long way since the days of teeing off on a mound of sand. So, if you're looking for a little extra warmth, or you're heading off towards the light, or looking to emerge from the darkness, now you know how it's made. Today on How It's Made. Fishing reels, answering a casting call. Miniature houses, model homes for the young and the young at heart. And kitchen mixers will bring you the ingredients from the factory in a special 2-part report. It's stirring stuff. But first, in the 12th century, the Chinese were the first to wind excess fishing line onto their rods before unreeling it back into the water. Today's reels are made with lightweight, high-strength materials and have gears to quickly deploy and retrieve the line, so you can catch bigger and stronger fish. Or at least try to. Antique reels are heavy and have just one speed. Modern reels have 2 or more speeds and fewer parts. To make a reel's frame, a computer-guided router cuts 4 openings in a cylinder made of aluminium. They let the angler access the spool inside the frame to undo any knots in the line. Another cutting machine shapes a stainless steel blank into a spindle, the inner part of the reel around which the fishing line winds. It also carves 2 pinion gears into the piece. The high gear retrieves the line faster. The low gear gives more power to fight big fish. The machine's cutters are made of carbide, an extremely durable material. Even so, they're changed on a weekly basis. Another cutter carves the reel's main gears, a high speed and a low speed. These main gears interact with the pinion gears to make the spool revolve. This lets the angler wind line back onto the reel. This cutter drills small indentations, part of the reel's drag system, which lets the angler adjust the line tension. The next cutter engraves the company name onto one of the reel's 2 side plates. Yet another cutter engraves the drag settings: 1, 2, 3, 4, and strike. Strike lets the angler fight fish weighing up to 900 kilos. The side plates are dipped in a series of chemical baths that bind a gold-coloured dye to their surface, a process called anodizing. Now, to assemble the fishing reel, waterproof grease and lubricant are applied to 2 safety catches that prevent an angler from using too little or too much line tension. A bearing is then added to support the spindle in the spool. click plate is also installed. This makes a sound when a fish takes the line. A stainless steel spindle sleeve and drag plate are added, as is a sturdy synthetic washer. The spindle and pinion gears are added to the spool. The spool is now ready to go into the frame. A rotating clamp steadies the reel, and the stainless steel fixture that attaches the reel to the rod is installed. And the left side plate is attached with 6 screws. This metal spring and plunger enabled the angler to change speeds from high to low with just the push of a button. A metal clip locks the mechanism in place. A little grease is added to the gearing, and the spool is fully assembled. It's inserted into the frame, and a harness lug is added. This lug will be attached to a fighting harness, worn to prevent a fish from yanking the rod out of the angler's hands. Next, the right side plate is mounted in place. A lever and a knob which will adjust the drag settings are added. The knob is turned clockwise for more tension, anti-clockwise for less. Next comes the installation of the stainless steel and plastic knob used to reel the line in. And finally, the button for switching speeds. The drag lever and the gears are checked to see if they engage properly. The reel is tested at high speed to see if the safety catch prevents what's called free spooling, a glitch that could send 900 meters of line flying wildly out of control. And that's a situation that would leave you reeling. For hundreds of years, dolls' houses have been hot property. At first they were built to entertain the children of the wealthy, but eventually mass production made these mini mansions widely available. Today they continue to be great places for childhood fantasies to reside. Any home building project is all about the details, but the details don't get much smaller than this. These dolls' houses are miniature versions of actual homes, made to scale. A large sheet of plywood is sliced into smaller pieces. For a consistently accurate job, a saw guide is used, which positions the wood for a specific cut. There's a different guide for each part. Using a hot iron, the company name is branded onto one of the foundation pieces. This doll's house will be sold as a kit. Here's a demonstration of how it should be put together. Back on the production line, the siding is being milled. This machine cuts furrows in wooden panels. This beveled effect mimics the exterior woodwork found on some houses. Next, holes for the windows and doors are cut using a router. And now the walls go up. Because this is a kit, each piece has to be a perfect fit. The first floor is installed and taped with masking tape while the glue dries. And now for the second story. It can take up to 100 hours to paint and assemble all the parts in a doll's house kit, depending on how elaborate the design is. Next, they raise the roof. This Victorian design has a two-part roof with a tower in the middle. Weight is added to apply pressure while the glue dries. This machine's protective cover has been temporarily removed to show its inner workings. A piece of pine is carefully fed in. It cuts the board into shingles, which fall into a bin below. Once the shingles are stained, they are hot glued to the roof, following a grid that was penciled on in advance. The roof is wrapped with tape to stabilize it while the glue dries. Back in the factory, 4 cutting wheels shape a piece of pine into mouldings that will be used for trim on various models. The door now goes on. It's been trimmed with some of the moulding we just saw being made. The windows also use moulding details. All this trim has been made on the same machine, using different cutters for the different profiles. This railing is a nice touch, and it will also provide support for the structure. All that's left is the interior decorating. Some people spend a small fortune on this stuff. Tiny toilets, chairs, even full kitchens in miniature. In this model of the home of Abraham Lincoln, the details are historically accurate. The pieces are packed carefully. Soon they'll make some child's dream of owning their own home come true. But first, somebody had better read the instructions. Coming up on How It's Made, we're all in a spin as we bring you a 2-part special looking at kitchen mixers. See you after the break. Welcome back to How It's Made. Whipping up a dessert used to take a fair bit of muscle power, until a mixer with a motor was invented in the early part of the 20th century. The first ones were very industrial looking and not much like today's sleek models. But with this invention, the job of baking is a piece of cake. Today's mixers can whisk you into a world of culinary delight. To make one, a machine straightens wire between rows of wheels. Computer-programmed forming tools make 12 bends to produce shapes, which will be used to build a whip attachment for the mixer. To assemble a whip, a technician fits the wire arcs into an aluminium hub, starting with the largest one and graduating down to the smallest. Underneath, a punch mechanism dimples the hub to fasten each wire to it. Here, dough hooks and beaters are dropped into a vibrating bowl full of metal nuggets. The friction polishes these zinc mixer attachments and gets rid of the sharp edges. Next, a band of aluminium is threaded into a machine that bends it to the contour of the mixer. This piece of trim carries the brand name. A bowl feeder now funnels hollow iron weights towards a system that threads wire through each one of them. Mechanical arms pinch and bend the wire, making small hooks on the ends. 2 of these weights will be used in each speed governor, the device which keeps the mixer's speed constant despite changes in the load. To assemble the speed governor, they arrange a brass hub, spring and a washer in a holding device and then press fit them together. The 2 weights are attached to the spring assembly using the protruding wires. The speed governor system is now complete. Here's how the governor weights fly out to regulate the mixer's speed. It's now time to prepare the motor shaft. This spinning steel cylinder is lowered to a revolving cutter. Lubricant keeps the cutter cool as it carves spirals into the end of the shaft. The spiraling grooves will allow the shaft to drive the mixer's internal gears. With its motor windings and bearings attached, the shaft is installed into the mixer body. Next, electrical contacts are riveted to plastic control boards. These contacts will conduct electricity to drive the motor. An electrical charge is delivered to the contacts to make sure they're working. Then, screws, nuts and springs are attached to complete the control board assembly. The control board will work in conjunction with the governor weights to control the mixer's speed. For these mixers to really shine, they'll need a good paint job. The mixer parts are polished on an abrasive belt to prepare them for painting. Then it's into the paint booth. This is a highly charged process. The paint has a positive electrical charge and is attracted to the zinc mixer parts, which are negatively charged. Now all the parts are in the mix. And coming up next, we'll show you how they all come together. Behind many a successful cook is a well-oiled machine that's made for speed. And that's the electric mixer. It produces the best results when the blades turn rapidly. If they turn too slowly, they won't mix the batter thoroughly. And that means your pastry could be a flop. To assemble this tilt-head mixer, a gear which will drive the attachments is installed. Next comes the stator, which creates the electrical field for the motor. A dab of oil is applied before the shaft and motor windings are mounted inside the unit. 2 motor brushes are slid into pre-drilled holes. The motor brushes will supply electricity to the internal components. This bearing bracket holds the motor in place. The front of it is lubricated and the electrical control board added. A trim band with the brand name on it is wrapped around the outside. Next, grease is poured into the section of the mixer that will hold the gears. The gear section will be sealed so the grease can't leak out. The other half of the unit, that already has some gears fixed to it, is attached. A drive pin that will move the whisk and other attachments is inserted in the shaft. More grease is applied to this section, and the 2 halves are screwed together. And then the planetary gear is installed. This gear will rotate the mixer attachments around the bowl. A pin is hammered in place to attach the planetary gear. A decorative ring is tapped onto the outside. The motor unit is mounted to the base, and an identification number is marked onto the bottom. Now the tilt head mixer goes for a spin. The next step is to adjust the speed. The technician installs a speed setting tool in the hub of the mixer. While the gears turn, he checks the readout and tunes it up. Each mixer has to be able to make a dizzying 200 rotations every minute. The hub is capped. The final step is to test the beater. It must be correctly positioned above the bowl. One last polish, and it's ready. Over at another station, a more commercial type of food mixer is being made. One with a bowl that lifts to the beater instead of a tilt head that lowers to the bowl. A base is screwed to a bowl support piece. Then the lower housing for the beater motor is attached. As the mixer moves on a conveyor, the motor and gears are installed. A generous squirt of grease is used to lubricate the transmission. And then the top of the motor is encased with more housing. Continuing down the line, the electrical speed controls are installed and topped off with more housing. The signature piece of trim is wrapped around it. The wattage and speed are checked using a probe. It passes inspection and it's ready for packing. It's taken approximately 10 minutes to assemble this mixer, but it's been made to last a lifetime. And with such a wide range of attachments for these mixers, you really can go stir crazy. So, whether you've fallen for this item hook, line and sinker, or this little miniature marvel makes you feel more at home, or perhaps our look at a classy kitchen gadget has you all in a spin, now you know how it's made. Today on How It's Made. Manhole covers, fitting a round peg into a round hole. Range hoods, removing those unwanted nasty niffs. Artificial logs, the secret behind those fiery fakes. And snowmobiles, a far cry from a one-horse open sleigh. But first, manhole covers are those metal lids on maintenance holes in the road. Workers lift them to enter and repair sewers and other underground utilities. Foundries make the covers out of heavy-duty cast iron, so they last for decades and don't budge under passing traffic. This company makes hundreds of models of manhole covers and collars, the rims upon which the covers sit. They come in two types of cast iron alloy. Either ductile iron, which has magnesium to reinforce it, or grey iron, which is just as strong but heavier. To make the cover, they first have to make a mould. This one's got the design of the cover's top carved into it. Workers pour in 300 kilograms of sand, mixed with glue and a hardener. For the underside of the cover, they repeat the step in another mould. A worker creates a channel in the sand mould, through which they'll pour the molten metal. He plugs the hole with a wooden block to preserve the cavity beneath. He removes the block and briefly reinserts the pipe to ensure the cavity hasn't caved in. It takes about 15 minutes for the sand mix to harden. A machine then inverts each box and vibrates to shake out the mould. To make one manhole cover, workers will join moulds of the top and bottom sections. Alignment lugs and glue between the sections help them align properly and form an airtight seal so molten metal won't leak out. Next, a machine flips the bottom mould, moves the top mould into position below, then mates the pair. The factory buys scrap metal from demolition sites and also recycles its own. It'll melt these metals with certain minerals to enhance the mix. Graphite to make it malleable, silicon to make it stronger, and magnesium to make this batch of ductile iron lightweight yet strong. Here a giant magnet picks up chunks of recycled iron and steel. The metal is preheated to 420 degrees Celsius, then transferred to a furnace. There at 1500 degrees Celsius, it takes about half an hour to melt enough metal to make 35 covers. Workers then transfer the molten metal to a cauldron and add more silicon. This evens out the consistency so it's easier to pour. Besides the channel for pouring in the metal, some larger moulds have vent holes to evacuate burning gases. It takes about an hour and a half for the metal to harden. A conveyor then drops the moulds into a container and breaks them open. Using a hook, they pick up the casting. This one's a collar weighing about 100 kilos. They knock off the remaining bits of sand and excess bits of metal that form during the casting. These scraps get recycled into a new batch of iron. Manhole covers vary in size according to the specifications ordered. Most are roughly the diameter of a car tyre. The average weight about 63 kilos. A worker now smooths out the edges of the collar and then the perimeter of the cover. This way it'll sit flush on the collar. This machine tests the strength of the cover by applying pressure. Each 2.5 centimetre area must withstand the weight of a car. They paint the covers and collars by dipping them in a bath of black tar. Once dry, the pieces have a rust-resistant finish that lasts for decades. And we expect them to last, especially as we have to drive over them every day. It wasn't until about 1800 that metal stoves with flues vented steam and smoke outdoors. Today, factories make encased fans that powerfully ventilate and also light the hob of your oven. The range hood sits above your simmering masterpiece, removing nasty niffs from your kitchen. No matter how well you cook, steam and smoke are inevitable. Fortunately, the range hood's fan clears the air in seconds. Production begins with this computer-guided machine. It cuts out a sheet of galvanized steel to make part of the hood's housing. A 300-ton press then perforates the sheet and cuts out up to 50 openings for screws, wiring, and exhaust outlets. Another panel for the housing is inserted in a 25-ton press. The machine bends the steel in 2 places. This component will be used to make a circular channel that evacuates smoke and steam, which often contains grease particles. Another machine with 3 rollers forms the circular channel that fits around the blower to direct air out through the exhaust. Here, a spot welding machine joins 2 corners of the hood's housing. This is mainly for aesthetics. A weld looks better than a screw or bolt. This 80-ton press bends the hood's shell, making one of 8 folds that gives the component its final shape. A plastic coating that protected the steel during the cutting is removed. A sticker with a product ID is applied. Then, a pad printing machine marks the brand name, one of 12 this factory produces. This is the first of 8 stops on an assembly line. A transformer is installed to power the blower's motor and 2 halogen lights. This circuit board regulates several functions, including 3 light intensities and the blower's 4-speed motor. The board is attached to the housing with 3 screws. This panel has lights that indicate which functions are active. Next, the blower's 165-watt electric motor is installed. The motor attaches with 3 screws into rubber bushings that reduce noise. Then, light sockets made of heat-resistant plastic are attached. The blower's housing snaps into place around the motor. A little silicone on the housing ensures an airtight seal around the blower. Then the blower wheel is installed. The lights are tested. Pressing this button 3 times increases the intensity of the light. There's 1 button for each of the motor's speeds. After a panel is snapped on to enclose the hood assembly, a plastic ring is attached to direct air through the blower. A computer system tracks each model's assembly. When workers complete a step, they input it into the system. An optical scanner also senses when they remove a part from one of 25 cubby holes, like these removable air filters made of mesh aluminium. The tracking system is called poker yoke, a Japanese-inspired method that ensures thorough assembly. It follows each model until workers place it in a box for shipping. The system's final task is to ensure that the guarantee card and installation manual are put in. Once the box has been stapled closed, a machine with suction cups picks it up and stacks it on a pallet. All this work so you can stay in the kitchen even if you can't stand the heat. Coming up on How It's Made, artificial logs. We'll answer the burning questions. And snowmobiles, a very cool way to travel. See you after the break. Welcome back to How It's Made. If you're in the mood to light a cosy fire, there's no longer any need to put on your coat and boots and trudge through the snow to the outdoor woodshed. Nowadays, you can buy a box of man-made logs. The environmentally friendly brands pollute less and are safer for your chimney. And it means a lot less hassle for you. These artificial logs are made entirely of compressed sawdust. Their moisture content is less than 9%, compared to 30% in real firewood. The compression and dryness combined makes these man-made logs easier to light than real ones. They don't throw sparks while burning, and they produce 300% more heat than real firewood. The high temperature burns up the gases better, so the logs emit up to 50% fewer pollutants. And they produce fewer ashes and far less creosote, a highly flammable tar that's a natural byproduct of wood burning. Creosote buildup in a flue can cause a chimney fire. The sawdust comes from pure natural hardwood, mostly oak and maple. The log company buys it from factories that make hardwood flooring. As the sawdust is clean and the log factory doesn't add chemicals, it's safe to cook over the fire. The moisture content is so low because the wood it came from has already been dried in huge ovens to make the flooring. The sawdust arrives in different consistencies, so the first step is to put it through a grinder to make the particles uniform in size. The next step is the key one: compression. At a rate of 2,500 kilograms per hour, an air-blowing system moves the sawdust from the grinder directly into a compression machine. The machine is a giant cylinder with a piston that moves inside. The piston compresses the sawdust using extreme high pressure, 1,400 kilograms per square centimetre. The result is a 12-metre-long compressed sawdust log. Unlike some other brands of artificial logs, this one contains no binding agents, which can pollute the air. The secret to making the sawdust stick together is the high compression. The intense heat it creates bonds the natural resins in the sawdust. As the log exits the compression machine, a cutter shapes a flat edge. This is a safety feature. With the flat edge on the bottom, the logs are easier to stack in the recommended 3-log configuration, and they don't roll out of position. Now a guillotine chops the 12-metre log into 40 smaller logs, each one 30 centimetres long. A separator pulls them apart. The company also produces a 27-centimetre log. The logs drop onto a conveyor belt that leads to the packaging area. The factory boxes its logs with instructions and 2 fire starters. The starters are made of sawdust and candle wax, much more effective than using newspapers to get the fire going. Other artificial logs can break easily because they're less dense. But not these ones. The high density of this company's logs translates into more burning time. 3 logs will keep your fireplace alight for about 3 hours, by which time that fella's hand might have stopped aching. Snowmobiles are widely used in the Arctic, but the small population makes for a small market, so most snowmobiles are produced for recreational purposes in parts of North America. The number of snowmobiles in Europe is still relatively low, although they're catching on as a cool way to travel. Snowmobiles need a rock-solid build to keep the riders safe and comfortable as they often travel across rugged terrain. It all begins with an aluminium alloy frame. The pieces arrive partly assembled to the radiator. The robot spins and positions the frame. A computer-guided machine punches holes and inserts rivets directly into the frame with great precision. The process bonds the parts tightly so they can't vibrate. Next comes the rear suspension, aimed at making the ride as smooth as possible. Inserting this plastic slide into the runner minimizes friction between the track and the suspension. A conveyor belt carries this suspension system through several stations. Wheels and sprockets will turn the track that grips the snow. The suspension kit, with springs and coils, goes directly into the runners. Along with these shock absorbers, the suspension will fit snugly into the snowmobile's frame. For now, everything is tightened manually. Assembling the transmission system starts with this countershaft. First, a high-performance brake disc made of forged steel is installed. The chain case fits snugly on top, thanks to the ridges on this ring. This die-cast aluminium casing will house 2 gears and a chain. This bolt connects to a spring that keeps the gears and chain tight as they turn. The chain tightener must slide smoothly back and forth in its groove to keep the chain's tension even. This test checks that the spring expands and compresses properly. Now comes the oil gauge. It's essential that oil lubricates the parts thoroughly, because the motor will generate a great deal of friction. The transmission fits on top of the frame. These coils, springs, runners and wheels fit easily into the rubber track. The rear suspension system connects to the track system, while this white plastic sprocket connects the track to the transmission. The speed sensor attaches directly to the sprocket. Four high-grade steel bolts anchor the rear suspension system to the frame. They're so strong that the suspension can withstand the vibrations that come with high speeds. Now for the engine assembly. Bolts attach the electric starter directly to the engine. The fuel-injected engine generates a lot of heat, up to 700 degrees Celsius. This shield has layers of insulating wool that act as a heat barrier to protect the rider. The engine's made of cast aluminium, so it's relatively light, just 45 kilograms, and it propels the snowmobile up to 200 kilometers an hour. Now for the front of the snowmobile. This front suspension system requires a different assembly from the rear one. A hoist brings it all together. The petrol tank is made of lightweight molded plastic rather than metal. They install the throttle assembly and a few more functional details. These lightweight aerodynamic plastic side panels give this snowmobile a sleek look. And now, the final step. The zero-gravity hoist lifts it all onto a pallet. Polystyrene sheets protect the snowmobile during transport to the retailer. From start to finish, it's taken 3 hours to assemble this showroom-ready snow-traveling machine. So, whether it's metal and round over a hole in the ground, or practical and strong, preventing a nasty pong, or perhaps it's not quite real, but heating you a great deal, now you know how it's made.